three. in the music. Good morning. So welcome everybody to the ADAS meeting here in Cape Town. We're about to begin our first session following the tutorials we held yesterday. So I'd like to begin by asking the chair of the Programming Organizing Committee, Kathleen Labrie, to say a few words. Kathleen, are you there?
Can you hear me?
Yes. Can I ask people in the room to turn down the volume on your laptops, just so we don't get any feedback? Go ahead, Kathleen.
Yes. Here we go. Sharing. Here we go. All right. So yes, I'm Kathleen Labrie. I'm the chair of the ADAS Programming Organizing Committee, and I really want to welcome you to ADAS 31. I wish I were there with you. Trust me, I wish I were there with you. But it's going to be for another time. Hopefully next year we're back to normal. So I just want to take a few minutes to acknowledge a few people. I want to acknowledge the Program Organizing Committee. We're a nice group of people distributed around the world, all type of fields, all type of organization. I encourage you to go to the adas.org website and go see the list of those fine people there who helped put the program together this year again. About the program, all the themes came from you and from the local organizing committee. The POC did the final grouping of the similar suggestions and the final selection. All the oral presentations, the contributed talks, were selected completely author blind again this year. It worked again very well. Once the votes were tallied, we looked at the representation distribution and adjusted a bit so we could meet our minimum diversity requirements. This is the second year of the ADAS Prize for Outstanding Contribution to Astronomical Software. Our winners this year are Doug Tody, Lindsay Davis, and Frank Valdez for the design and development of the core RF system and science packages. So congratulations. Frank will give a talk on Thursday, I believe, towards the end of the conference. And if you wonder how this came to happen, earlier this year, all the POC requested nominations from the ADAS community, and the POC then voted on those nominations that came from you. And if you hear the little meowing, that's my cat, because that's reality these days. Public service announcement. Don't forget to submit your proceedings and go to the website for the instructions. And I have to congratulate Stelog. They did a fantastic job. Special kudos to Carolina and Nikki. And a big thanks to Russ, who got the ball rolling, and then to Oleg, who picked up that ball and just ran with it. And he did run with it. Thank you all. And I want to thank our hosts. So the Inter-University Institute for Data Intensive Astronomy, and then the Center for Radio Astronomy Techniques and Technology, the NRF and SAAO, and National Research Foundation and South African Astronomical Observatory. Thank you very much for hosting us. And with that, it's Oleg's show. Go for it, take it over. Thank you. Have a good meeting, everyone.
So it's quite a privilege to open this thing. I do have special feelings about ADAS because ADAS 2 was my very first conference. And then ADAS 3 was my second conference, and then ADAS 4 was my third conference, and then ADAS 5, and well, you get the pattern. Eventually, I discovered other meetings. Not all of them were as good, and I have to say none of them were as strange as this one. You know, this is very weird. This is the first time I'm actually seeing someone live for 2 years almost, and obviously we have no idea how to organize a hybrid meeting. So ask me again in 4 days if it worked or not. Bear with any problems in the meantime. But especially I have to say a big thanks to our international guests for turning up, because if you hadn't turned up, it wouldn't be a real meeting. Even if you didn't turn up for the opening remarks, it's still okay. Now that you have turned up, let's please be careful. We gave you 2 masks in your conference bag, so keep your masks on. COVID is still with us. Keep your mask on unless you're eating, unless you're drinking. ADAS stands for Software and Systems. The SS is for that, not for super spreader, so let's be careful. So about the structure of the program, you will see the schedule is a little bit unusual. As a reward for making it to Cape Town, we wanted to give you the opportunity to get something out of it. So we're going to work hard every morning from early on, but you're free from lunchtime, and we only expect you back here for dinner. So you've got the whole day to explore Cape Town and make the most of it, and please do, especially if you haven't been, because there's so much to offer. Logistics, so we are providing dinner for you, not lunch. So for lunch, you're free to go today. For dinner, you get back here, and dinner is going to be served at 7 upstairs on the ground floor restaurant, the same place you had breakfast. And that's going to be all days except Wednesday, because on Wednesday we have the conference dinner, which is going to be at the aquarium. So on Wednesday, we're going to give you lunch here instead after the morning sessions. And then we meet you at the aquarium. Don't be late because it should be super special. What else? Toilets are in the back here, behind the stairs. And I think that's pretty much it. Please enjoy the conference. And I would now like to yield the floor to our 2 observatory directors. I think Dr. Rob Adam is going to go first, who is Managing Director of South African Radio Astronomy Observatory. And now I yield the floor to Rob.
I believe I'm in the which doesn't make sense to me. Yes. Okay. Thanks very much, Ruby. Anyway, good for a second time. Good morning, everybody, and thank you, Oleg, for inviting me. And thank you. Well, sorry, it's good to see Russ again here in South Africa after such a long time. So it was kind of a welcome surprise for me to see him on the screen there. I'm going to share my screen. I've just got 5 minutes or so of slides, which I hope will tease out some of the issues that seem to pop out for me with respect to this conference and what one might get out of it. Let me just... Is that clear to everybody? You see? Thanks very much. Let me just move my top there. Okay, this is the propaganda slide where I explain what SARAO is, the South African Radio Astronomy Observatory. It's a national facility of the National Research Foundation, formerly SKA South Africa, combined with the Hartbeespoort Radio Astronomy Observatory to form SARAO. It's the primary science and engineering interface with the international SKA organization, observatory, and is responsible for South Africa's contribution to the infrastructure and engineering aspects of the SKA radio telescope. Also responsible for development and management of the Karoo Observatory site, design, construction, and operation of the Meerkat Radio Telescope, and coordination of all radio astronomy initiatives and facilities in South Africa and African partner countries. In other words, the countries that joined us as part of the SKA bid. Geodesy and VLBI activities at the Hartraw facility, the African Very Long Baseline Interferometry Network, guest instruments which have been contributed by international partners, such as the S-band receivers which came from Max Planck, the Breakthrough and Listen equipment which is allowing commensal observations with respect to SETI, and then also human capital development to ensure successful operation of all facilities within the organization. The proper scientific exploitation of the facilities, where we generally we support radio astronomy at the universities through being a national facility. Obviously, we do have our own radio astronomers, but most of the users of our facility sit outside in the universities. And the commercialization of intellectual property developed within SARAO. On to Meerkat, our main facility. It's currently the most sensitive radio array telescope in the world. 64 13.5 meter dishes, designed by South African scientists and engineers, built with more than 75% local content. It was heavily prototyped, which I think was the reason for it performing so well when it was finally built. Construction budget, 3 billion over 5 years, roughly 3 billion. Key technical specifications were exceeded by a factor of 2 for no additional cost, and I think that was the benefit of doing the engineering and the prototyping right. Delivery milestones on schedule, recognized as a key infrastructure project of the South African government. It's an SKA precursor. In other words, SKA is in several phases. This is effectively phase 0. We're about to begin phase 1 construction. It's an engineering prototype, but also intended to do early science. With Meerkat, we were able to build up science and engineering teams in South Africa, to build Meerkat and SKA and also to use them. Currently, over 200 engineers and scientists employed. The Human Capital Development Program to grow and diversify the science, I mentioned that in the previous slide. Also developing industrial capacity in South Africa to compete for SKA procurement packages. Finally, Meerkat will be incorporated into SKA Mid and make up 30% of its collecting area. Getting on to data, I mean, I guess all of you are familiar with the kind of data architecture which a radio telescope array has, but quantitatively, into the correlator there is pouring 2 terabits per second. That's processed in the Karoo Array Processor Building, so CSP, STP, some archive, and then out of that goes 20 gigs per second into SANREN, in other words, this is the network that comes down to Cape Town, into the Center for High Performance Computing, into the Meerkat archive, and then it goes to other so-called Tier 2 centers, one of which is IDEA, the Inter-University Data Intensive Institute for Astronomy, which Russ represents. The different phases of this, I've said that Meerkat into the correlator goes 2 terabits per second. The SKA1 mid equivalent of that is 25 times higher data rate, 50 terabits per second. And SKA2, well, that's not really even properly conceptualized or designed yet, but the estimate is up to 5 petabits per second. Into the science processor, 0.7 terabits per second for Meerkat, 20 for SKA1 mid. Into the archive from Meerkat, 20 gigs per second, SKA1 mid upwards of 300. Compute load for Meerkat, 200 teraflops, SKA1 mid probably 30 plus petaflops, significant upscaling. Okay, here I get to my issues. that I would really like some thought given to over this meeting. More than ever before, astronomy has become a data-intensive science. The torrents of data coming out of MeerKAT are unprecedented. The SKA will take this to an even higher data rate, as I've explained. Our relative inability to process this data timeously is proving to be a bottleneck in taking the science forward. In a previous era, handing over the data cubes to the PIs was sufficient for telescope operations to contribute. Now it isn't, and further refinement is necessary. Probably 10 years ago, when we conceptualized how MeerKAT would work, we were living in an era where astronomers, so-called black belt astronomers, were able to cope with the data rates that came off instruments fairly easily. You didn't have to do any hand-holding. But nowadays, although astronomers crave data, they don't always know what to do with it when they get it. There are various mitigating measures for this challenge. For example, IDEA, which I've mentioned, is supposed to help address this challenge with respect to MeerKAT, to provide the refinement to the data so that real science can actually be done. And the global network of regional science centers aims to do the same for the SKA. So those are kind of current operational challenges which we're busy with. I mean, we even had a crisis in terms of the archive recently, because the data was queuing up and it wasn't being utilized. So we'll have to rethink that and capacitate the PIs more than we're doing at the moment. I'm just going to end off with having said that, this is really the end of my talk, just to show you a couple of pictures. Those of you that haven't seen the MeerKAT array, there's 64 antennas. You see in the top right-hand corner the Karoo Array processor building and the dish assembly shed. The processor building is probably the biggest Faraday cage in South Africa, so that none of the electronic interference gets out as radio frequency interference into the environment and thereby swamps all the signals we're trying to observe. Been on the cover of National Geographic already. The most exciting thing for me, or one of the most exciting things, is it was designed and constructed in South Africa, MeerKAT. All of these engineering facilities are South African engineering facilities, largely in the Joburg area. There's one of the dishes being lowered onto the pedestal, and then on the right-hand side you can see a dish, the backing being assembled, and in the dish assembly shed, we could fit 4 dishes into that shed simultaneously. This is a clip from the launch of MeerKAT, and one of the take-home messages from that launch was that astronomers were astonished that MeerKAT worked straight out of the box. And I think the reason for that was that it was done right from the beginning with systems engineering approach, so that we looked at the interfaces between the different subsystems, made sure that those articulated and worked properly together. That was our Bragg picture image at the launch, which is you're probably very familiar with it, but it's a radio image of the center of the Milky Way, our galaxy, 25,000 light years away. And the reason that that's a Bragg picture is that it's very bright from a radio perspective, and it's a bit like, from an optical perspective, taking a picture right into the sun and getting some clarity out of it. There's Xi Jinping, Premier, next to our President Cyril Ramaphosa. There have been a number of industrial spin-offs. I won't go into all of them. This is just a list over there. But just to, for example, there's a passive radar system which has been developed using local FM radio broadcasting in order to locate aircraft which we don't want flying over the site. And then to me, the most interesting, so in the last year or so, was the development of 20,000 continuous positive airway pressure ventilators, CPAP ventilators, in response to the COVID-19 pandemic. And to me, the lesson for that was that if you've got a really good balanced team of engineers, you can aim them at almost any engineering problem and get a good outcome. You don't have to recruit in a topic-specific way if you've got that kind of balanced team, particularly with the systems engineers in place. I don't want to go into all of these examples. So, yeah, that's the Center for High Performance Computing, Innovation and Mass Data Storage. This is and the SIRAO innovation. To show you the impact we're having on young astronomers, this was the 2018 Postgraduate Scholarship Conference, Port Elizabeth, I think. Without the SKA initiative and SIRAO, none of these youngsters would have been there and in fact have been in radio astronomy, or at least a very small fraction of them. Thank you very much, Oleg, Ruby, Russ, all of you, for listening. And over to Petri now, I guess.
Thanks. Yes, good morning from me as well. And as Oleg was saying, thank you for having a hybrid conference. It is amazing to see actually 3D people in a meeting after such a long time. So thanks for the organizers. Thanks for inviting me for this welcome. So I'm really welcoming you from SAO perspective, and having an opportunity to say a few words of what we do as SAO. So do we have the slides on? Oh, there you go. Okay, so just a little overview of what we do, some pre-pictures. And those of you who are not in Cape Town, and just to make you jealous, hey, so this is a pretty picture of Cape Town from where the observatory is. So right in the foreground here, this is the old historic SAO observatory, or what used to be the Royal Observatory, and the hotel where we're now sitting, those of us here in physical presence, somewhere over there. And yeah, I'm really hoping that those of you visiting Cape Town get to see around. And our observatory is the older one in this context. It was actually founded 200 years ago. We celebrated our bicentennial last year, October, about this time. 1820, it was already established, although we've been the SAAO for about 50 years now as a South African national observatory. As Rob was saying, we are also a national facility of the NRF, National Research Foundation, so we're sister organizations with SIRAO. This is a picture from our headquarters there, a few kilometers away. And it's full of historic telescopes, that side as well. There's a picture of the McLean telescope against the Table Mountain in the background there. And yeah, again, it's a fascinating place for history. This telescope, amongst many other things, it actually, oxygen was discovered in stars with this telescope. I forget the year exactly. I think Christian, sitting in the audience, probably would know. But there's a lot of history there. But then the modern astronomy that we do is the core is in Sutherland. So essentially the optical infrared astronomy on this whole continent, by far the biggest concentration is within our observatory, but the telescopes since 50 years have been growing up on the Sutherland observing plateau about 400 kilometers away, obviously because of light pollution, right? And just to put that into context, for those of you who are not familiar, so we're here in Cape Town, Sutherland is there, and we were just seeing pictures that Rob was showing of the Meerkat, which is then further up in the northern Karoo. And the reason why the optical telescopes are in Sutherland, you can see from the satellite picture, it really is a dark site. It is one of we have measurements now for many years of baseline. It's just as dark as the Atacama places, Paranal, essentially as dark as it gets anywhere on the planet for optical astronomy. And it's protected by legislation as well in South Africa, which is absolutely great. The same thing as the radio quietness protection over the radio facilities. And about 40 of our 140 staff are stationed in Sutherland. And let's see, yeah, so SALT, Southern African Large Telescope, is the largest of the facilities there. It's an international collaboration, but South Africa is the largest partner. We have partners from US, UK, Poland, India. It's been, first light was about 16 years ago, something like that. I forget now exactly, or 17 even. Yeah, in fact, one of the people in the audience over here, David Buckley, he was who oversaw the whole building and science operation of it at that time. And yeah, we're in the 10th year of full science operations now, 10th or 11th year right at this moment. It's fully service mode operated, which means massive software needs, requirements for data delivery, data acquisition, data delivery, proposal management, all of that. And this was the first such big software attempt in coming up with the system for a large telescope in South Africa. And it's working very well at the moment. And hoping that you're hearing more of that kind of things during the week. Let me just, there's absolutely no time to go into science, what SALT and SAO as a whole do, but I just flash one slide on the kind of the bigger topics that we do, because in addition to being a facility which provides these telescopes for the community, both South Africa and internationally, SAO, we're also a research institute ourselves, so we do research, we do student supervision, PhD students, master's students, and by and large, I would put our areas into transient science, galaxy evolution, which really leverages the very dark conditions of the southern sky. We're getting into exoplanet science and then computational astrophysics. And it's really that first part, transients, which gets to something that I want to say in a moment. Okay, we do multi-wavelength astronomy. We've done already simultaneous observations with MeerKAT, for example, the SAO telescopes, and SALT. There's one telescope in particular in Sutherland called Meerlicht, which looks at which shadows fully wherever MeerKAT is pointing, this telescope is looking at in the optical, which is the first on the planet. Well, not in the daytime, right? So, radio astronomers have the advantage of looking at the sky in the daytime, so we do it in the nighttime. But wherever MeerKAT is pointing at the nighttime, Meerlicht is looking at. So getting fully continuous coverage in multi-wavelength aspects. And not only radio and optical, but others, of course, as well. I should mention just briefly that the birth of multi-messenger astronomy, that epic event a few years ago when the first electromagnetic counterpart of a gravitational wave was discovered, 2017. Our observatory was right in the thick of it with multiple telescopes on the site involved in that search. And what we're very proud of was that the SALT spectrum was actually the first proper spectrum of that event. This is from that paper with 4,000 odd authors. So the very first timed spectrum was actually from SALT. Okay, and then finally, of our kind of mandate, what SAO does, we do technology development as well. We have, Rob mentioned this National Ventilator project, for example, a kind of an offshoot, spin-off of what we do with our skills. And it was actually our workshop then who produced with the high precision mechanics capabilities of our workshops, the prototypes of those oxygen blenders. But yeah, software, optics, electronics, control systems, a big part of our organization is doing that. And one of our visions is to start building instruments for other observatories or missions during this decade, not only for us, which we do already. And a big part of what we do in the future is addressing the future of astronomy, which is, for example, the Rubin Observatory LSST surveys, massive data amounts, deluge, and not only the quantity of it, but the speed, the pace of how data come. And that's why we have this concept that have been thinking of for a couple of years now, called the Intelligent Observatory, where this capability that we have in Sutherland of having multiple telescopes, there's 20 odd now, some of our own, but many hosted, but then South Africa has slices of the time, different kinds of instruments, making that work in the one holistic network, intelligently connected, so that when you do follow-up or when you do surveys, you don't do it individually and with human reaction timescales, but autonomously, automatically. Something happens on the sky, there's a data trigger, broker intelligently selects what should be observed, which instrument should be used, which kind of telescope, which size of telescope, all that happens in a split second, and then the commands go. So that's what we're building. And there's a very specific roadmap for it, involving things like remotely operable telescopes, service mode robotic capabilities, and I won't go into details of this because there's going to be a talk about this in a couple of days' time. But one of the big successes of big successes of the last 2 years during COVID time is that we converted once and for all the Sutherland telescopes that we own and operate into remotely operable ones. They've been operated from Cape Town by the SALT Ops team. There's some new developments on robotic capabilities on the old ancient telescopes as well. Oh, I should mention that some of these telescopes really are old, 80-year-old technology, 50-year-old technology, and you retrofit them to be first remotely operable and then robotic capabilities. And that's actually awesome. It's sometimes harder to do that way rather than building it initially. But I just point you to Steve Potter's talk on Wednesday morning for the Intelligent Observatory talk, because this is at the core of our vision, what we want to do. And I'll finish there. And I really wish you a very productive and great time in this conference and in Cape Town, those of you visiting. Thanks.
Thank you very much, Petri, and thank you, Rob. I think your remarks have given us a very good perspective into why and how South Africa has emerged as a leading provider of data and software systems in just a few short years to the global community, and why it's very timely to have the ADAS meeting here in Cape Town. So now we're going to proceed to the first talk of the session. Lo, did you have something to say?
I just wanted to comment on the upcoming talk. The speaker we're gonna hear a recording of the talk by the speaker, but the speaker is online and live, and she's going to answer comments in the live questions channel. So you're gonna see quite a bit of this during the conference. We're experimenting with this format. So start asking questions on Discord and live questions, and the speaker will be answering you as you hear her doing the talk.
Thank you, Oleg.
My name is Kumiko Usuda Sato from National Astronomical Observatory of Japan, NAOJ. Thank you very much for giving me a chance to present Galaxy Cruise, NAOJ's very first citizen science project using big data. At first, let me introduce myself. I am an astronomer doing public outreach. Until June 2013, I have lived on the island of Hawaii for 15 years and have done extensive outreach activities for the local community. In 2013, I moved back to Japan and worked at NAOJ headquarters in Mitaka, Tokyo. During these 8 years, I have worked to make astronomy resources inclusive For example, we renewed the Solar System Walk, the 1.4 billion scale model of the solar system. Look, this is the Earth station of the Solar System Walk. We put a braille label for blind and visually impaired people and also added English explanations. In addition, we developed audio guide for visually impaired people and sign language guide movies for hearing impaired people. We also created a tactile model of the Sparrow Telescope, NAOJ's large optical infrared telescope located in Hawaii. Both visually impaired people and sighted people can touch and understand the telescope. Since 2017, I have worked to initiate the NAOJ's first citizen science project using the big data taken by the Sparrow Telescope. How to design our citizen science project, called Galaxy Cruise, is today's main topic. The targets of inclusive astronomy and citizen science may look different, but both activities are for including diverse people in astronomy. Now, I came back to Hawaii and started working at the Sparrow Telescope again as a public outreach specialist. The Sparrow Telescope is an optical infrared telescope operated by NAOJ near the summit of Mauna Kea, Hawaii. With its 8.2-meter large primary mirror, the Sparrow Telescope collects faint light from outer space. One of the Sparrow Telescope's most prominent feature is Hypersh Prime Cam, HSC, mounted on the prime focus, the top of the telescope structure. HSC has an epoch-making wide field of view for an 8-meter class telescope, as large as 9 full moons. The right photo shows HSC mounted on the prime focus. It is a giant digital camera as tall as an adult. Since 2014, HSC has been conducting unprecedented large survey called HSC SSP, Hypersh Prime Cam Subaru Strategic Program, spending 330 nights. In the vast cosmic images, many galaxies are captured. As you can see, galaxies have diverse shapes. Number 1 is an elliptical galaxy with a round, featureless shape. Number 2 is a spiral galaxy with spiral arms. Number 3 is also a spiral galaxy, but something is different from number 2. What is the difference? The spiral arms of number 2 have a symmetrical structure, but the upper right of the arm of number 3 is partially distorted. When another galaxy passed by, the arm was pulled out and distorted by gravitational interaction. We call this kind of galaxy interacting galaxy. Number 3, number 4, and number 5 are interacting galaxies. Number 4 is called the tadpole galaxy. Gravitational interaction made a long tail-like structure like tadpole's tail due to a galactic encounter. We call number 5 the jellyfish galaxy. Two spiral galaxies are interacting and affecting their shapes with each other, this galaxy and this galaxy. Why do galaxies show such diverse shapes? How are galaxies formed and evolved? They are one of the big unsolved questions of astronomy, and galaxy interaction and merging are thought to be the key. To solve the mystery, researchers cannot classify galaxies captured with HSC all by themselves, because too many galaxies are captured. So we started up the citizen science project, Galaxy Cruise. As you may know, citizen science is a scientific work by members of the general public, often in collaboration with professional scientists and scientific institutions. Citizen science is beneficial both citizen astronomers and professional researchers. Citizen astronomers or non-professionals can access and enjoy the latest high-quality big data used by researchers and contribute to their research. Researchers can obtain a large amount of data classification results that cannot be accomplished by themselves. Look, this is Dr. Masayuki Tanaka, the captain of Galaxy Cruise, a galaxy scientist of Sparrow Telescope. To initiate the very first citizen science project of NAOJ, these 6 members gathered. The project team consists of a researcher, software engineer, web designer, and public information and outreach specialist like myself. I am a project coordinator or a herdsman to control the whale of the cruise ship. Okay, let's set sail for the cosmic ocean on Galaxy Cruise.
Set sail for the cosmic ocean. You can see various types of galaxies. How did such a variety of galaxies come to be? Therein lies the history of the universe. Let's start on a journey to travel around many galaxies.
Okay, Galaxy Cruise has the following unique features. Number 1, citizen astronomers can easily enjoy the world's top quality big data taken with HSC of the Sparrow Telescope. Number 2, unique world view with some gamification events. Our project is likened to a cruise ship to explore the vast cosmic ocean. The HSC data consists of 4 small and deep observational fields and 6 wide fields. In Galaxy Cruise, we call small fields towns and wide fields continents. When a citizen astronomer completes one town or continent, a departure stamp is added to a passport. Also, citizen astronomers can collect souvenir illustrations. The lower image shows the cruise map or a nautical chart. This is a symbol of the world's view of Galaxy Cruise, arranged from the Sparrow Telescope's observation map. Number 3, we developed the 3 steps of training menu. Citizen astronomers need to complete the training sessions to obtain a basic knowledge of galaxies and classify galaxies with confidence. Also, they compare their classification results with their captains at the practice course after logging into the welcome page. Number 4, the welcome page is based on HSC map, with which researchers to take an overall view or a bird's eye view of the vast cosmic image. HSC map is a kind of Google Maps HSC version, and citizen astronomers can explore the cosmic image freely. The world's view and role-playing of the cruise ship and detailed training menus are the unique components of Galaxy Cruise. The 3 steps of the training menu can make non-professionals confident in classifying galaxies. When they complete all training sessions, they can get a boarding pass. This role-play and gamification event can allow citizen astronomers to sign up as crew members. After citizen astronomers are on board, we actively send information. On the first day of every single month, we publish a news article on the homepage to provide the updates of this project or a science-related topic about galaxies. Sometimes when they log in, they receive a message from the captain. In messages, the captain reports his updates and sends appreciation to citizen astronomers. We also provide Classify 1,000 Galaxies in 1 month campaigns in summers and winters. Now I will show demonstration of the Galaxy Cruise website. This is a home page. When you scroll down, you see some news articles. When you click Training, you can start 3 steps of the training menus. Lesson 1, 2, 3. Lesson 1 is the easiest one. You will learn the difference between elliptical and spiral galaxies. After you learn, you have 5 questions to check your knowledge. When you finish answering all 5 questions, click Go to Lesson 2. In Lesson 2, you will learn what are interacting galaxies. After you learn, you have another 5 questions. When you finish answering all 5 questions, click Go to Lesson 3. This is the last lesson. You will learn features of interacting galaxies, and you have 5 questions again. When you complete all training sessions, please click here. I have completed all the training sessions. And then, congratulations, you get the boarding pass. With this boarding pass, click here and go to the login screen. Actually, I already have the account. And this is the welcome page of Galaxy Cruise. I mean the classification page. You see some green rectangles. Inside of the rectangles, the HSC data is hiding. Put your cursor inside of the rectangle, and using a mouse or touchpad, you can zoom into the rectangle. And many dots gush out. These dots are galaxies. When you go deeper and deeper and deeper, more and more galaxies come out. So you can explore the vast cosmic images captured with HSC of the Spiral Telescope freely, like Google Map. This is the function of HSC map. When you want to start classification, click this ship whale, and a galaxy is displayed in the center of the screen. Same as lesson 1, 2, 3, you will answer 3 questions per 1 galaxy. The first one is same as lesson 1, spiral or elliptical. Okay, and sometimes you can zoom in and out to see the galaxy clearly. It looks an elliptical galaxy. Click here. Number 2, same as lesson 2, interacting or not interacting. So you see 2 galaxies very close to each other and they share halo. So I'm sure it is interacting. Number 3, as lesson 3, the feature of interaction. It looks distortion, and then click submission. And the next galaxy is displayed. You repeat this process. When you click this settings button, you can change the color with full color or grayscale. And Wait a moment, please. Go back to color, and you can change the contrast. Dark, normal, and bright. Okay, close the setting button. And this is the passport, your passport. When you finish a town or continent, you can add a new passport stamp. And this is your voyage log. So when you finish one town, an anchor mark is displayed. And when you finish a continent, the continent is colored in brown. And these are special items during the campaign. This paper bag shows souvenirs you already collected. When you finish a small area of a town or continent, you receive some souvenir icons. When you make a screenshot, just click this camera icon. This is the welcome page of Galaxy Cruise. Let's go back to the slide. The Galaxy Cruise Japanese site opened on November 1st, 2019, and the English site opened on February 19th, 2020. As of September 1st, 2021, 7,769 seasoned astronomers from 84 countries and regions have registered. About 70% are from Japan, followed by Malaysia and Russia. As of September 1st, 2021, the total classification results exceeded 1.9 million, almost 2 million. The campaign with exclusive digital items really works to increase the classification number. From July 1st to 25th of this year, we conducted a survey and received 248 respondents. This graph shows the average rating among 171 active users about how much each item motivated them on a 5-point scale. Beautiful images captured by the Sparrow telescope was rated most positively, followed by 3 training menus and Cosmic Voyage Themes welcome page. Among the media for providing information, monthly news articles were highly rated. We are very happy to know that active season astronomers gave a high rating for Galaxy Cruise original or most featured items. This graph shows the average rating among active users as Group A in blue color, about how much each item motivates for Season 2 we are now planning. Non-active users as Group B in orange color rated the same item as motivating for coming back as an active user. Both groups gave the highest rating for videos of researcher. Before we conducted the survey, the captain recorded the latest scientific analysis results, and we released the video in September. Based on the survey results, we will keep disseminating information to citizen astronomers. Today, I presented how to design our citizen science project, Galaxy Cruise, to engage and motivate citizen astronomers. I think the following 4 items are the key components supported by the survey results. Number 1, beautiful images captured by the Sparrow telescope. The accessible and easy to handle world's highest quality big data motivates seasoned astronomers to participate. Number 2, detailed training menus. We know that many seasoned astronomers are not sure if their classification results are correct. Giving them confidence enables them to keep contributing to scientific research. Number 3, Cosmic Voyage Themes welcome page and gamification. the role play as being a crew member and receiving messages from the captain keep their motivation. Number 4, interaction with citizen astronomers. We provide the latest information through news articles and captain's messages and video to keep them motivated. Campaigns also work well to increase classification results. We will keep considering easy-to-handle web design and frequent interaction with citizen astronomers. In future, the captain and we will proceed with the scientific analysis using the classification results from citizen astronomers. At the same time, we are now planning the season 2 with fainter galaxies. Number 3, furthermore, we are planning the machine learning of AI, artificial intelligence, using the classification results of galaxy clues as the training data. My talk is that's all. Thank you very much for listening.
Thank you very much, Kumiko. We have some questions on the live question feed and the Discord application. I see that you've been answering them as they come in. So if anybody has any more questions, please enter them into the live question part of Discord. Did you want me to read the questions out? That's right. Yeah. So if you haven't got access to the questions, I can summarize questions. There was a question from William O'Mullane, but how many galaxies has the HSC imaged? And the answer is about 20,000 bright ones in season 1, and in season 2, an additional 20 to 30,000 fainter galaxies are expected to be added. Michelle Lochner commented that the idea of gamifying the process was a good one, and wondered how many questions for classification are done compared to the Galaxy Zoo. And the response was that the question 3 is much simpler than the Galaxy Zoo, and there's 3 questions per galaxy. And then Kathleen Labrie asked, what is the minimum age that's recommended for participants? And Kumiko said that they had some elementary kids, school kids participate in the cruise with their parents. So there really is no age limit in that sense or recommendation. I think that's the question. Are there more questions? We have another minute or 2 for questions if there are any more. Yep. Okay, if there are no more questions, thank you again, Kumiko, and we'll go on to our next. Our next speaker is Tim Hostetler, speaking about web accessibility trends and implementation in dynamic web applications. It's also remote.
Hi. Access as possible. So accessibility is a huge part of that within our applications. Every year, WebAIM holds an accessibility survey of the top 1 million websites. In this table, it sort of shows some of the top errors that they found using their tool, automated tool. You can see that year over year, there's pretty consistent numbers. There's always a lot of errors. And these errors are actually pretty simple things to fix. And it just kind of goes to show that even a really small amount of effort can make a huge difference as far as accessibility for somebody who uses these types of tools to access the web. And so it would be great if a lot of these websites were to fix a few of these things. It would really make a big difference. As far as web accessibility goes, there's really one main standard, the Web Content Accessibility Guidelines, WCAG, it's also known as. It falls into 4 main principal areas and 13 main guidelines, and then there's so many success criteria underneath each of those. To quickly kind of go over these, perceivable, in here we want to make sure that at least we're providing one alternative way for users to access any information. For example, any non-text items like images and icons should always have some kind of textual element alongside it in order to give screen readers information about what it is exactly. Under operable, we want to make sure that all our content is accessible by multiple input modalities. For example, anything accessible by a mouse should also be accessible by a keyboard, touch input, voice control, that sort of thing. And that's pretty important. We want to make sure that, in understandable, we want to make sure that text is readable, understandable, presented in a clear and predictable way. We always have text in the same spot on the screen, for example, that doesn't change. We want to have proper contrast, line lengths, line heights, things like that, to make sure that text is readable and really just content in general is able to be understood clearly for anyone. And under robust, here it's just talking about having our markup have the proper structure so that tools, current and future tools, can use it without a problem for maximum compatibility. So just to give some basics, there are a number of semantic tags already built into HTML that can help screen readers understand what's going on. And so just talking about page structure, there are a few main semantic tags that you can use: header, main, nav, footer. There's also a side. There's several other semantic tags, but basically these will provide some structure to your web app that screen readers can grab onto, and they know how to handle each one of these sections, at least contextually. WebAIM, however, in their screen reader survey actually noted that the main way people seem to want to navigate is using headings instead. And so that's also another important part of structuring your website. Using headings, you can actually lay out all of the different sections on your site, and you can use them to have a hierarchy of content. And screen readers will actually list all these out for users, and they can skip through them very quickly. And it provides a great way of adding little jump points all over your site so that they can get the content quickly and they aren't stuck trying to wave through lots and lots of things that aren't important to them. Also, just to mention, headings are only tags, so they can also be hidden from the screen if that makes more sense in your layout or something, and read directly to screen readers. And so if, for example, here in the top element, we're showing that heading, but for the search results below, it's hidden and only shown to screen readers. You should also always be providing text alternatives for non-text items. For example, the first item here is an icon link. This one by itself wouldn't be read or would have no information at all for a screen reader, even though it's a link. So we want to make sure there's some kind of text there that's going to be shown to the screen reader when it's focused upon. And then the same goes with the image below. we have an alt tag that will be read by the screen reader to give some context as to what it is exactly. So ADS is a single page application, which really means that the page doesn't refresh very often, which can pose a really unique challenge for screen reader or for accessibility. And we really, because we need to let the screen readers know that something has changed on the site, since we have a lot of dynamic content changing. At the bottom here, you can see in this example that we actually have a line of text under the search bar that shows the number of records returned. And on its own, prior to any changes, this is just a generic kind of element that has no real meaning to a screen reader. So it wouldn't know to read this to a user. However, it's actually pretty important information. So, and you can even see here in the Chrome accessibility tools that it shows its role as just a generic tag with no particular special abilities. With a really simple change, by adding an extra role status to this, we can change it to be a live region. In this case, it has the live region setting as polite, which basically means that it's going to kind of let the user know in a timely manner, but not necessarily interrupt what else they're already doing. But what's neat about this is that when content changes inside of this element, for example, when we do a new search, screen readers will alert on that and let users know that your search returned so many results, for example. Another area where these are really great is in error messages. So, for example, here we have an error message that shows up after doing a query. Same problem as the number of results element before. This one's really just a generic tag. And so with a really simple change, changing that to role alert, in this case, gives the live region an assertive setting, which basically will interrupt the user if they're listening to something else on the page and let them know that there was an error here. And at least it gives them an idea that something happened. Otherwise, they may not know. So to quickly mention, there are a few tools that are pretty great. AxDev tools and Wave are two automated tools that you can use that are just extensions that you can download. These will provide some good feedback. However, there's no quite analog for using the real tools that users are using. Things like JAWS and NVDA and VoiceOver are the main screen readers. Also Orca for Linux. And JAWS is as a paid one, but the other three are free, for example. And using them as much as possible is really important. Beyond screen readers, really, though, you want to make sure that you're trying out some other kinds of extensions that users might use. For example, there's one for dyslexic users that will modify the font a little bit to help with readability. There's also tools that can help with zooming in on text or maybe fixing line heights and things like that they do in more of a global way. You want to make sure that your site can handle those kinds of modifications without breaking the flow and still be able to understand what's on the page. Another tool that I've used is Chrome Lens, which helps with seeing what your page looks like at different levels of blindness and also color blindness. So I wanted to briefly mention that we also participated in a sort of third-party accessibility audit through Harvard Web Publishing, which we contracted out to. it was actually very helpful. They provided a great detailed report for us, and it was a great learning experience. They're getting some outside perspective was really important to us since we didn't have the experience in-house. So we really recommend doing this, and it was helpful for us to give us a good starting point for making changes. So in closing, for those of you out there building or maintaining web apps, I would say you should make sure that you're always thinking of accessibility as part of the core design, and it should be a main part of any new application, for example. And to do the basic stuff, make sure you have proper markup and a good structure, and you're following those guidelines. And as much as you can, learn the tools and use those automated tools to help you. And as often as possible, do usability and accessibility testing, especially with people that actually use these tools. That's where you really will find how it actually will look to users whenever they attempt to access your site. So, thank you.
Thank you, Tim. We have time for a few questions. If you could post your questions on the live question channel on Discord. Anybody has any questions? Oh, I see a question coming, I think. Tim, can you see the live question channel yourself?
I see it, yeah. Thank you.
Okay. So do you have any favorite tools?
We definitely use Wave and Axe DevTools for doing just general accessibility testing. I would say there are ones that you can use as part of your automated sort of setup in your CI. I don't think we have a real good setup right now for that, other than using just the automated tools. So I don't know if I can recommend one that's built in for CI, but I'll look and see what we're using and post it on here.
Accessibility impaired astronomy community. It's a question from Mark
We actually
Taylor.
haven't gotten any specific feedback from the astronomy community in general, but we know it's an important issue, and would really like to, would love to have more conversations about that. Users that use these tools and ADS would be great to find out how they get along using the website.
Okay, we'll take one more question. How often do you update your database for newly published papers or ATELs?
I'm not sure about the answer to that one.
Yeah, I can imagine. Okay, so maybe we'll take any more questions offline, or online, I guess, in this case. And we'll move on to our next speaker. Thank you again, Tim. Our next speaker is Fernando Leventura, speaking about unsupervised learning approaches to classifying extended radio sources with Meerkat.
Good morning. Today I would like to present a unsupervised learning approach to finding exotic radio galaxies in Meerkat MDCLS data. So, first of all, why do we want to do this? Well, as you know, modern and future surveys produce a lot of data. New instruments such as Meerkat and the SKA produce massive surveys that have tens of thousands, if not hundreds of thousands of sources, and extracting what we want out of that manually is tedious and unfeasible. So, the data we're using are from Meerkat, from the MGCLS survey, so legacy cluster survey in the radio spectrum, and here are, so just briefly what we're looking for. So we are looking for radio galaxies, and we're not looking for the more normal FR1 or FR2 type galaxies. So of course, Van Riley class 1 and 2. Then there are more interesting ones such as bent-tailed and egg-shaped, and we want to find the more exotic things here. So, and of course there's some cluster emission that also comes up a lot in these images. So we are looking for the more unusual sources. So an autoencoder, briefly, is an unsupervised learning approach where we have two neural networks, one of which takes input and tries to map it onto some latent space as an encoded form, and then the decoder is some form that takes the encoded form and tries to map it back into the original image. So training can be done unsupervised because we can compare the input image to the reconstructed image, and then it can compare that without human intervention and backpropagate the errors through the neural networks. Special pooling layers are a layer for a neural network that will remove the influence of sizes of the images. We want this because, again, the apparent size of a galaxy in a survey is not going to be relevant to its morphological classification because it could be any distance or due to the, the size of it. So that shouldn't really affect classification, and pyramidal pooling layers remove the influence. So they are a feature reduction layer. They reduce down our data. So here's basically what it looks like. So you have an autoencoder, takes the input image through a pooling layer, regular convolutional layers, encoded form, decoder tries to reverse that. So we will train the autoencoders on the more usual images, like FR1s and FR2s. So hopefully it will learn to reconstruct these really well, which means that when it gets something more exotic, it will struggle to reconstruct it, and we can then use that to detect these unusual images. Finally, ensembles. So ensembles are where we basically tie the autoencoders together. We use the variations between multiple autoencoders, in our case 3, with different latent spaces. So the restrictions we place on the encoded form will determine how they behave, and then this can produce better results. So how did we prepare our data? Well, first we take the Meerkat images, then we use a software called PyBDSF to extract or find the relevant sources. PyBDSF will tell us which sources are point sources or Gaussian blobs. We don't want those, so we remove them. And then we take the selected images, run them through another rough filter, trying to extract sort of point source type things, because we don't want those. We then take cutouts. We manually label these for our training and testing purposes. And then because manually labeling didn't produce, obviously, a lot of images, we augmented the images by rotation, because again, flipping and rotation, that should not affect the classification, because the galaxy can obviously be oriented in any way on the sky. And this produced about 3,000 images for training, so this is quite a small data set, and I should mention that already. So here we have the results from a single convolutional, from a single autoencoder. Now these are the so in each, at the top we have the training, the best reconstructed training data. In the middle, the best reconstructed typical data, which is what we're not looking for, which it should reconstruct well. And at the bottom, the best reconstructed exotic images. So the bottom 2 rows are testing, and in each big row, the row on top shows the original, and the row below shows the reconstruction. So you can see here already that FR2s, it does tend to do very well, and the exotics, which it is reconstructing well. So these are the ones it will have the most difficulty finding, do tend to be exotics that have a more traditional sort of lobe structure. Now these are the ones it has the worst reconstruction of. So as you can see, it struggles with contrast, so really low contrast images, it struggles to reconstruct. But notice the exotics at the bottom. See that the ones that it most struggles to reconstruct are the ones that look the most different from sort of FR1, FR2 type structures, your sort of galaxy remnants and that sort of thing. And so it means that finding these is the easiest. These are the easiest things to extract from it. Even so, here is the distribution of the reconstruction. So we use the normalized cross correlation as a measure of reconstruction. And as you can see, the distributions of the exotics skews more to the low end, as we would expect. However, both peak quite high, which means that separating the two is not that good. And as you can see, it does have some effect, but the F1 score is still, which is a measure of the recall and precision together, is not too high. However, let us now look at what happens when we use an ensemble. So we have here 3 autoencoders that have their output combined in 2 different ways. On the left, we have the average reconstruction error tested against the threshold. But on the right, we test each reconstruction error against the threshold individually and then allow them to basically vote on the classification. And as you can see, that gives us a massive performance improvement, because you can see the classification here is way better. And obviously, we cannot just pick the best threshold, so the threshold would be determined through testing, because you would not know the best threshold for your data. If you did, there would be no point in this. But we can get an F1 score above 0.9, and that's actually, this is a massive improvement over the previous generation. But I should mention again that this is quite a small data set, and this is a new avenue we're exploring, and although it shows a lot of promise, more testing definitely required. So, yes, if we look at the receiver operating characteristic and the confusion matrix for it, we notice that actually they have, it's performing very well. And definitely this is the avenue we'll be exploring going forward, is looking at the ensemble using a voting type mechanism to determine which are exotics. And of course, I should say that here our categories are quite broad. So we've been trying to separate typical sources from exotic sources, but that's very broad. So if we train this on something more specific, like if you were trying to say find only egg-shaped sources and you trained it on everything that's not an egg-shaped, you could have a more accurate performance. So the way this would be used is it would be imperfect, but it would present you with a lot of candidates for what you want. And you will use it doesn't go back. Sorry. So you would use the candidates that you would then manually search. So it would not be you would not just take it at its word, but if you are looking for something specific, you can use it to find the best candidates for whatever it is that you're looking for. And it's very fast. So running this once it's trained, running this on tens or hundreds of thousands of images is relatively quick, and we can definitely much more easily find the candidates of whatever study you're trying to do. You can process in a day, you can get enough candidates for your study, when previously you would have to manually spend weeks perhaps manually classifying these to find your ideal data. So going forward, this is the approach we'll be exploring, and I hope you can agree that it shows a lot of promise in finding exotic sources in radio galaxy data. Thank you.
Thank you, Fernando. We have a few questions on the live question channel. Some of them are from people in the room. If you'd like to ask the question directly, please go ahead. Please come to the microphone at the front of the room.
Oh yeah, so you spoke about how you use PipeDSF to first remove all the compact emission. So what happens in the case where the compact emission is part of the exotic structure that you are trying to classify?
What happens when it's, so you mean if it's part of the source? Yeah, so how PyBDSF works is it finds the bright points in your image, and then it finds an island around that image. So it will find the bright point, and then it will include as part of the source anything around it that has above a certain contrast ratio. So if the source was, if it's part of the source, it's typically connected by some diffuse emission, and that emission should then be above the threshold, and it would return that as a single source. What we were removing there were things that were unconnected. So if it tells us, here's a bright thing, and maybe there's some emission around it, but it's just a blob and nothing connected. And it is also not perfect, so.
Thank you. Michelle Lochner, are you in the room?
Cool. Thanks. Thanks for the great talk, Fernando. It's basically a follow-up question. I didn't really follow, because we know PyBDSF kind of sucks at source finding, especially for the extended sources. No offense to everyone who loves PyBDSF, we all love it, but the source finding step is often the hardest, and there's often a lot of manual work that has to go into actually identifying this is one single source. Like often you'll have several, it'll see the same source as several different sources. So I just missed a little bit. Like I get throwing away all the compact sources, fine, but how did you actually build a curated training set? And there's also the issue of sources being on very different scales, for instance. Yeah. So I'm kind of interested in that step and how much manual work that took.
Okay, so after we took PyBDSF, it does still return, so we put it on almost a mode of rather return more sources than fewer. Yeah. So a lot of point sources and blobs were still included in that, even after that step. And as I say, it is imperfect, so we weren't trying to create a definitive catalog of every source in this image, just enough for our testing purposes. But after that, ran a rough filter, sort of trying to fit a Gaussian to it, and if it was successful enough, throw it away as well. And then it is manual. And in the manual process, so to create our set for testing, that was very manual, and so as I say here, the manually labeled images, to create the labeled images, that was a manual process. And what we had was, we had like an interface, and you could select different categories for the interface. And there were certain buttons for PyBDSF has messed this thing up, throw it away, or this should not be included, or PyBDSF got something wrong, reprocess this image. So yeah, you're right, it does have a lot of errors, but it was just a way to basically cut down the work before we went to the manual labeling. So
yeah, that's completely understandable, and I'm in the same boat with my stuff. But I think it's a step that we have to fix if we want to really automate these methods and find good ways of doing it. Definitely. Yeah.
So I mentioned we had about 3,000. So the testing and the training sources together were about 3,500 or 4,000 images. But what PyBDSF had returned to us was like 5.5. So of that 5.5, after we had gone through them, only like 3.5 were actually used. But that's still, okay, yes, you have to go to 5,500 images, but then that's not 100,000 images. So, yeah.
Sure. Cool. Can I ask another question? Or do you have other questions on Slack?
Short one.
Okay. Just very quickly, did you have a look at the latent space and see if you could gain a bit of intuition about what it's trying to learn from the galaxies?
So I have an extra slide just in case someone
well
asks this.
Prepared.
And I accidentally went to it, but yeah. So this is the latent space. So they are quite high dimensional, as you can see. Yeah, they are quite high dimensional, but we use PCA, which is just a way of projecting data down. And as you can see, there's some separation. The exotics are in red, but nothing really. However, they were not really set up to separate things necessarily. So, yeah, we did look at the latent space, but we were not necessarily expecting anything there, and we didn't find anything there. But we did have a look at them in PCA just to see in case it did something.
Did something.
But yeah.
Okay, cool. Thanks so much.
So we have two more questions on the channel.
Okay.
First one from Simone Riggi. What did you do to handle the background sources, e.g. the point-like sources? Did you detect them with PyBDSF and then mask them or replace with background? Or did you only compute the loss on Galaxy pixels or both?
So we actually tried a couple of approaches. We did try to mask them out with PyBDSF detections, but it didn't work very well. And then in the end, what we did is we just took a very close cutout of the source so that, you know, any nearby but not quite background sources were excluded. And then anything that was too obscured by background sources, we did not use for this. But mostly the source that it was posted into the machine was just a close cutout of the source itself as it is found in the, with no additional masking. Although we did try various approaches for that, and then eventually we just decided this was the best way to do it.
Thank you. And one final question from Dirk Petrie. How exactly do you determine whether the autoencoder is struggling to reconstruct?
Sorry?
How exactly do you determine whether the autoencoder is struggling to reconstruct?
So after the reconstruction, we take the reconstructed image and the initial image and calculate the normalized cross-correlation, and then we apply some threshold value to that. So if it's too, you know, so it's like a reconstruction error. It's just based on the physical image. So if it's too high, if it's, you know, if the reconstruction is good enough, then we assume it's something that it was taught to reconstruct, so a typical image. And if it's poorer, then we assume it's something exotic.
Okay. And there was one final question came in. Do all the cutouts have the same size, and how did you choose this size?
Okay, so as I mentioned earlier, we have the pyramid spatial pooling layer, which will take any apparent size, and it's meant to be a pooling layer that is invariant to the size and will reduce the effect of the size on the classification. So when we had our cutouts, they were all different sizes because, you know, obviously in the image they're all different sizes in the galaxies or in the cluster image. So the number of pixels eventually that gets passed in is the same. It's just a high number that's high enough to accommodate the various resolutions, but obviously some of them are still low resolution, but the pyramidal spatial pooling layer is meant to take care of that, to allow us some invariance in the size, or the resolution rather, for the encoder purposes, to make sure that's not what it's classifying on.
Okay, thank you very much, Fernando. Thanks again.
Thank you.
So that's the end of our first session. We're now going for a coffee break till 10 o'clock time here in South Africa. See you all again in 25 minutes. So I'm finished now. Somebody else is taking over.
My thought was that people would like so.
Okay, thank you very much. I hope you enjoyed your tea and coffee break and Gather Town. This next session, we start with welcoming Jonathan Kenyon, who's giving us an in-person talk about Cortical, an embarrassingly parallel calibration using Numba and Dask.
Thank you so much. Yeah, so as mentioned, I'm Jonathan Kenyon, and I'm going to be talking to you about Cortical. I'm currently a postdoc affiliated with Rhodes University and Soreo. Okay, just to start off, I know not everyone in the audience comes from a radio interferometry background. So what do we mean when we talk about calibration? Well, simply the process of correcting a measurement or system to ensure that we get the best possible data out. And specifically in the context of radio interferometry, we're usually talking about solving for and correcting the complex valued antenna gains. An example of what this might do is shown on the bottom of the slide. The left-hand image you may see is an image prior to calibration, and the image on the right is post-calibration, and you can see there's a pretty remarkable difference. So the motivation behind this is that modern instruments and, of course, astronomers require that calibration has to be increasingly flexible, fast, and user-friendly. And to those of you who've designed software, there's always tension between these requirements, and it's very difficult to have all three. In particular, in the context of the 5 Vs, the volume and velocity components are very difficult to deal with, and I hope Rob's introduction earlier convinced you of that. So just to provide some context as to what radio interferometer data looks like, we have a standard format called the measurement set. It's columnar storage backed by CASA tables. These typically consist of rows and labeled columns, and those columns may somewhat peculiarly contain n-dimensional arrays. Typical data dimensions will be row, which is a combination of time index and baseline, and that will be in the hundreds of thousands to millions. Channel, which is typically between a few thousand and tens of thousands, and correlation typically between 1 and 4. The table on the bottom of the slide is just an indication of how much data you expect to come out of Meerkat in an hour in about 4K and 32K mode. Bear in mind that this is an underestimate, as it doesn't record all the auxiliary information that also has to be stored. Okay, so well, what is Cortical? It's the spiritual successor to Cubicle. If you're not familiar with Cubicle, don't worry about it. It was calibration software I wrote during my PhD. It's a Python-based package, and it makes extensive use of Dask and Number. I'll get into that in just a moment. And it uses this measurement set-like data structure directly, which is quite compact in memory. The aim of Cortical is to be an all-in-one solution to calibration at scale. So this is a little bit of an aside. I'm not really here to talk about Cortical's features, more about the computational aspects of it. But just in case it is interesting to you, it supports chains of Jones terms, so those are gains, including both parameterized and direction-dependent terms. We have a robust reweighting scheme re-implemented, which can be used in combination with any gains. We have support for loading and interpolating gains for doing your 1GC. And at present, we have very rudimentary support for baseline-dependent average data, but that is very much a work in progress. And just in general, it is quite highly optimized and parallelized. Okay, so what is Dask? Well, the Dask docs themselves state that Dask is a flexible library for parallel computing in Python. It will be very familiar to you if you've used something like NumPy or Pandas. It has its own collections which mimic NumPy arrays and Pandas data frames. And these so-called big data collections can be used to compose task graphs describing a computation. And then those task graphs can be subsequently allocated to resources by Dask's internal schedulers, so you sort of relinquish the distribution components of the problem. Sort of by default, it supports both distribution and larger than memory computations, and because of this, you can scale from running applications locally on your laptop all the way onto a compute cluster with multiple nodes. So I always think a picture is worth 1,000 words. So I'm just going to take you through some very basic Dask syntax in the hope that maybe you see something that can help you in your application and development. So here I import Dask arrays much as you'd import NumPy. I set up an array of random data, just calling it data. The thing that may be a bit peculiar here is I also specify chunks. So unlike NumPy, where arrays will typically be a monolithic piece of data living in memory, Dask has this notion of chunked arrays. So these arrays are internally broken down into chunks which may be much smaller than the overall size of the array. We can then visualize these things in, say, an IPython notebook, and you can see that in block 2 on this slide. If I simply put the array in the cell, you can see that I get all sorts of interesting metadata out, such as the size of the array, the size of the individual chunks, how big it is, how many tasks there are in producing those chunks, the number of chunks themselves. So that's just to reiterate that chunked nature of the Dask arrays. And then also very interestingly, they're also lazy. And what we mean by lazy, well, if we print the contents of that array, you can see that it doesn't contain any numbers. It's just an array object that's produced by random sample with a given shape and a certain chunk size. And that laziness is quite important, which we'll get onto. So moving on, we can do operations on these Dask arrays. So for instance, in the top cell here, I take a sum. And again, this is still lazy. If I print the result, there is no result yet. It simply says that there's an array produced by the sum aggregate method. And here you'll notice it no longer has a shape, because if you sum an entire array, you expect to get a scalar out. And indeed, once we call compute, we go from being lazy to being evaluated. And then, of course, we get an answer out. What makes this quite interesting is if we move on to the next block, you can see that we can do things like map blocks, and this allows us to map arbitrary functions over chunks of an array. And so here, for instance, I'm taking the sum of each chunk rather than the sum of the entire array. And again, just visualizing it, it remains lazy, but ultimately we can call compute and we'll get a result per chunk of the input array. So just to summarize, we use Dask arrays to construct task graphs, which in turn are submitted to Dask's internal schedulers, and they handle allocating those tasks to various compute resources. The second technology in Cortical is Number. So from its docs, it states that Number is an open source JIT, or just-in-time compiler, that translates a subset of Python and NumPy code into fast machine code. So this lets you essentially get the speed of compiled code without compromising flexibility. You can get incredible speed-ups with very little additions, with very few additions to your code. The one caveat here is complex design patterns may be quite difficult to implement. So again, just to present an example, this is just a very simple Python function which determines the nth Fibonacci number. On the left, you can see the pure Python implementation. If we time that 100 times, it takes about 3.4 microseconds per call. On the right-hand side, you can see an example using Numba. In this example, all I do is import the JIT from Numba and then apply a decorator telling it that I'm not using Python and I don't need the global interpreter. And if I run that, you can see that it takes about 200 nanoseconds before. So that's a factor of 17 improvement after adding just 2 lines of code. The final piece of the problem is DaskMS, which is another Python package that exposes measurement set data as Dask array objects living in X-array datasets. On the bottom of this slide, you can see what that might look like. And unfortunately, I'm running out of time, so I'm going to skip over this. So just to show you some results, this is a small local experiment. This is only 2 gigabytes of data. The point here is not to see how this is operating at scale. It's just to give you an indication of its behavior. And you can see that these results are pretty good. So Cortical's results are in yellow, Cubical's are in blue or teal, and you can see that Cortical convincingly outperforms Cubical in both terms of speed and memory footprint. And again, just because I'm running out of time, I want to get onto the most important experiment here, which is now this is distributed. So this is a Meerkat calibrator observation at L-band. There's about 100 gigs of data here, so it's a lot more realistic in terms of problem size. We calibrate these and we compare wall clock times as a function of cluster size. There are some details about the cluster just there. And just in terms of calibration, this is just a single gain per time and channel. So what we can see on the left axis is the wall clock time, the right axis is efficiency. That's just measured as the predicted runtime you'd expect if a single node was the optimal performance. And what we can see is the solid orange line has the correct behavior. It's following the dashed orange line, which is the prediction. But unfortunately, it doesn't quite match. We're still digging into why that is the case. But what you should also be able to see is that our wall clock time comes down from around 20 minutes to under 3 for calibrating this calibrator observation. So we're pretty pleased with that. It's kind of proof that Cortical is successfully distributing and calibrating Meerkat scale data. And just a final thing about some caveats. I did not use the measurement set for these experiments. There are a number of reasons pertaining to the lack of thread safety of the measurement set and the fact that Python Castle Core, which is the Python interface to the measurement set, does not drop the global interpreter lock. This makes distribution incredibly difficult. And if you want to ask me questions about that, feel free. And then I'll just leave you with my conclusions, and I think it's time for some questions.
Thank you. That's very impressive indeed. So we've got a question that's come in from Discord, from Harrow, saying, am I responsible for making sure the chunk size divides into the Dask array size nicely? What happens if it doesn't?
So Dask doesn't require chunking to be regular. You can have trailing chunks that have a different size. You are responsible in that you need to know that your code does the correct thing if you get a chunk of an unexpected size. But you are not forced in any way to say, divide 9 by 4 and expect that to work.
Okay, thank you. And we have a question from Oleg. If you could step up to the mic, please.
Thanks. I'm very amused by all this Dask developments. I think it's absolutely great, and it reminds me of what we were trying to do with Mech trees with Jan, I don't know, 20 years ago by now. And one thing we already knew about then, but we had no idea how to address. Of course, the execution time of the graph depends very much on how you schedule the execution and which order you evaluate it on. So what if anything, is done about that?
So this is kind of a two-tier problem. So at some level, we do trust to Dask to do the right thing, but then at the same time, we know it doesn't always do the right thing. It's a two-pronged problem. So Dask has an ordering layer where it decides the order in which tasks theoretically should execute. And then inside its scheduler, it also has a decision-making process where it essentially goes, ooh, what am I going to do next? And what can actually cause problems is sometimes that process of going, what am I going to do next, will lead to it doing silly things because it's no longer doing the theoretically correct thing from an ordering perspective. Inside Cortical, we have written a plugin that kind of coerces it to do smarter things when running tasks. Essentially, what it boils down to is pinning certain parts of your graph to certain cluster nodes. So that you can be sure that Dask doesn't stupidly move tasks around unnecessarily.
Right, exactly, because data is distributed, so you really want to things stay where they are in the nodes. Okay, thank you very much. Cool.
Thank you, Jonathan. I think we're running out of time for questions, but there's one more question in the, and now two questions in the Discord, if you would like to go and answer them. Thank you so much again. Okay, our next speaker, Adam Zadrozny, is joining us remotely, and he will present natural language processing of astronomical transients reports. Interesting.
Okay, so I'm from National Center for Nuclear Research in Poland, and the project that we started to working is connected with allowing the computer to read what the astronomers to analyze the GCN circulars and astronomical telegrams and extract the data from it. Basically, many of the very interesting parts, the stuff that we are working on is a time domain astronomy. There are many phenomena that are very time constraints. And if you would like to get most of it, we need to get the data. And usually those hunting for GRB afterglows or for trying to observe the kilonova requires a lot of instruments. And over a very certain of time, the kilonova is a bit easier to catch because it's visible for a 60 centimeters telescope for more than 1 day. But with the short GRBs, the time to get the data is very small. And usually we got from the GRB satellites an information that there was a GRB, where it was. More or less we know the area, but then we need to handle them. For the most short GRBs, we don't catch the afterglow. Sometimes the important information about the position is covered in the GCNs, and the large observatories have the people on call to read GCNs, like they could do it live, but the small ones does not. And there is a gap because sometimes from the GCN you can learn, okay, there is the transient disposition right there, the candidate for the afterglow, or we check this area and we have the upper limit, so there is no afterglow in this area. But we cannot read it by the computer. Of course, and the project that I'm working on is try to allow the computer to get it. The GCN, when we, in the 90s, where we tried to hunt for the, I remember this when I was in the primary school, the people were trying to observe the first GRB afterglow. There was a GCN network connected, which allows the gamma ray satellites to send the information about the GRBs observed, and also to the telescope to send the circulars with the observations and what they observed. So here is there's also the astronomical telegram, which also allows to communicate the results of observation, not going through the peer review, which is very lengthy process. So if we look on this text, we have what we have here is it's basically a text that we observed that there is some position of the source, and we have some information about what was the exposure time, what filters were used, and so on. Similar stuff we have here with search for counterpart to IceCube with Antares and what we get here. This is really nice stuff if you are a human, but for a computer this is a nightmare, because this is written in a quite specific language, but still this is the language. It's not the data that we can just read through Python. And one of the most important cases when the going through the GCN was crucial was the observation of the trying to hunt for the first kilonovi. The swap was the first one to observe, and if the team were able to read GCNs, they got the observation at the same time as swap, maybe 1 hour later if it was in the observing field. But this event was unique if you look on the events that were delivered by the LIGO and Virgo detectors, because it was very well localized. The localization was really good. It's only 40 square degrees. In O3 we did not have such a great localization. We also did not have the GRB counterpart to any of the mergers of 2 neutron stars. But in O4 we expect to have a better localization, maybe not so good as in case of GW 170817, but still good. Okay, so how we can process the language? Basically, if we look on the reading the GCNs, we could the way that we approach it in the 90s to just chop it into the words would not work. What we need to efficiently do it is to use transformers. I would say that it's quite an old technique because it's from 2017 and it's now perfect. Over the time we are the people working on NLP deliver better and better models. But the idea behind using the changing the paradigm how we deal with the language with AI was to try to learn to teach the neural net, the huge model which have the millions of parameters hidden inside, to deal with language as a human. So, for example, to mask some parts and allow it to guess what the word was behind. But this allows to, if we train the model like BERT, if we trained on the gigantic corpus, then we can fine tune it for a certain task. For example, the question answering. So what we basically doing, we are asking a question to the text and trying to the neural model to highlight the part that is best fitting for our question in the natural language. So here we have the text regarding observation of the trying to get what was the redshift to the some GRB by observing the afterglow. And what we can get, we can ask the question in natural language, what was observed, and then we put the text of the GCN as a context to this question, and we can get, okay, the answer is optical afterglow, what are the position in text? So this is the position of this part in text, and how well it fits the question. Of course, it means that we put first the question, then we put a text that we are trying to ask the question to, and we got some answer from the text. Of course, if we formulate the question badly, so what was detected? It would be the continuum, but the reason why we got this answer is because here was a key phrase that we detect something, but the language used here was observed as a one. Okay, but if we ask another question, what was the redshift? We immediately get the answer that we can extract by using the question in natural language from GCNs. We can extract the viable data. What was the time of observation? So here we just got the information about the observation part. So why we are trying to build the pipeline for processing it? The key reason is that if we have the automatic telescope somewhere in Chile or in South Africa, and we are not having the people on call, the computer could read the stream of GCNs for observation of kilonova in 04 and notice, okay, here we got the upper limits, and the upper limits are better than the depth of our telescope. So probably there is nothing there. We cross out those fields, or there is observed some kilonova. So let's go there, get the data, get it fast, and this question answering pipeline, of course, on top of it, there needs to be put some additional filters, could interfere by reading the GCN stream with scheduler and saying, okay, those fields we cross out, to those fields we got, this field have a higher priority. But this is not all. We also could do the volume analysis of GCNs and ATOL. There is about 50,000 of ATOLs and about 300,000 of GCNs that we can do the analysis, the text analysis, and analyze this data by using the time and the volume, and maybe search for some patterns that we see, some variabilities that were observed and not linked because we could not efficiently processing the language. The efficient language processing is only last 4 years since the transformer models came into play. But what I would like you to get from the talk is that it's clearly possible to read GCN circulars and astronomical telegrams by computer. Our project will be publicly available as a Python package quite soon. And to analyze the language, we need the transform-based models to do that. And at first, we can use the BERT model for question answering, but it would not be enough. It has to be trained for the domain-specific language. We need to add also some stuff on top of it. Yes? Okay.
Okay, thank you very much. We have some questions that have come in on Discord. James is asking, would creating machine-readable standards for the additional/extracted metadata avoid the need for multiple groups to rescan the archive?
Yeah, it would, but the problem is, the key issue is that sometimes you need to add some commentary if you get something unusual. And yes, of course, the machine-readable standards will be nice. There is some formulation of text that are much easier to read by machine than others. But still, we have the GCN archive, and we could dig through this. We cannot change what was going. We cannot reformulate the past stuff, but in the future, yeah, we probably will have some machine-readable standard that would be better. But for now, for 04, I guess it might be highly important to have the tools like that.
Thank you. I think we'll get one quick question and then we'll move on. There'll be more questions in Discord for you to answer. So Sergi asks, how do you train and evaluate your model with astronomical data?
Well, this is with the language. If we have the model that it's generally used for the question answering, then we need to prepare the additional set of questions and answers from the GCN text to additionally fine-tune the model.
Okay, thank you very much again. Our next talk is recorded, but the speaker is online, and so we'll be able to answer questions. It's Christopher Zappart, and the talk is Julia Meets Big Data, JVO Experience with Distributed Computing.
Hi, I'm Christopher Zappart from JVO at NOJ, and well, today let's talk about Julia. Today's talk is not only about Julia, it's also about big data. Now, for the purposes of this presentation, let us define big data as datasets that cannot be processed by a single computer. Basically, we are talking distributed storage, distributed computing. Well, we just need a supercomputer. Now, SKA guys, please do look away. The largest publicly available ALMA FITS file is only about 350 gigabytes. So we are nowhere near SKA's 256 terabytes of data. But then again, ALMA 2 is on the horizon. Such big datasets almost invariably require remote viewing. There is just no way anyone can download terabytes of data to their own computer within a reasonable timescale. As most of you might have been aware, at JVIO we have been offering a way to preview FITS files in a web browser for, well, quite some time, occasionally presenting our work at ADAS. And there is also the new kid on the block, the new Carta Viewer, which is really like a Swiss Army knife. And now, after churning through very many different programming languages, we at JVIO have been busy working on a distributed supercomputer edition of FITS WebQL coded in Julia. But before going ahead and talking about Julia, here are a few words about the one major difference between our FITS WebQL and the new Carta Viewer. Well, basically, when you view a 3D FITS data cube via FITS WebQL, you're presented with a single 2D image built up based on all the frequency channels present in the data cube. This means a lot of work on the FITS WebQL part, since we need to go through the entire dataset at least once. If it's 1 terabyte of data, we go through 1 terabyte of data. Carta, on the other hand, may seem faster on large datasets, and this is for a good reason. They do not read all the data. Carta only shows you one 2D image corresponding to a single frequency channel. So even for 1 terabyte large FITS files, they only show you one small part of the big picture. This is the main difference. Carta, less work but no overview. FITS WebQL, we do more work so that you can see the big picture. We have finally come to the Julia part. Well, guess what? Paul Barrett has already introduced everyone to Julia. Thank you, Paul. So here's my take on the subject. Julia is typically positioned as a faster and better alternative to Python. Just like Python, it is interpreted. But here's where the similarities end. Unlike Python, out of the box, Julia gets compiled down to the machine code like C or Fortran. Well, personally, I think of Julia as Fortran on steroids, and this is for very good reasons. To start with, arrays begin at 1, like in Fortran or Wolfram Mathematica. You've got vectors and matrices working out of the box, and you can broadcast a scalar function across a matrix, just like in modern Fortran. But unlike Fortran, you can also do low-level systems programming in Julia. There are mutexes and spin locks, hash tables, web development tools, and most importantly of all, strings just work. Fortran is infamous for having multiple string implementations that never quite seem to work properly. Well, does Julia actually work? Well, see for yourself. So here we are, a supercomputer edition of FITS WebQL. And there is a Julia logo, so yes, we are running on Julia. And we are using a small cluster comprising of 4 desktop computers. So let's open about 80 gigabytes of data. There you are, and the real-time spectrum display is quite smooth, no problems here. And we can show you data frequency channel by channel as well as streaming video. So now here comes the big test. Let's open 350 gigabytes of FITS data. And here we go. It's all in RAM, and the action is quite smooth, as you can see. So the question is, why do we have such large data sets? Well, the answer is that each individual frequency channel, well, it corresponds to a 2D image about 11,000 pixels by 11,000 pixels, and there are 700 such large frequency channels. So this is the reason why we've got about 350 gigabytes of data. So here we are looking at some major scientific programming languages. At JVO, Rust has been working great in the production environment for the last 3 years. However, when it came to trying it out on a small cluster, I have run into some serious problems with the various messaging libraries, for example, ZeroMQ, or especially problems with the NanoMessage library. So switching over to C++, well, yes, you can actually write memory-safe programs in C++ in a Rust manner. You just end up with a spaghetti code full of lambdas and smart pointers everywhere. Seriously, though, C++ feels much slower compared with pure C. And I have had some problems with the ever-changing new WebSockets networking library as well. Plus, there are no native matrix variables available in C++. So in comes modern Fortran 2018. Core Fortran to be exact. Well, Fortran is not bad at all. As you well know, Fortran has been used on supercomputers for many decades. It is still in use in NASA, and it does its work very well. The newer additions like CoreArrays make it easy to do distributed computing on clusters. Unfortunately, core arrays are not concurrent, they are not asynchronous. So you cannot serve requests coming from multiple users at the same time. There's more on that on the next slide. So finally, we have turned to Julia for help. I first used Julia about 3 years ago, but it was quite unstable at the time. 3 years is a long time. Right now, Julia has got very stable. And most importantly, it's got fully asynchronous distributed computing. Plus, it offers a very productive development environment as well. So these are the main reasons why I have finally settled on Julia. Here's a slide about some shortcomings of Core Fortran. Well, basically, all requests have to be processed sequentially. So you can only handle request number 2 after finishing the previous request number 1. Request-response pairs must match precisely. This isn't a problem in a scientific computing application. But when you look at a typical web application, requests come all over the place at different times. And whilst some requests can be handled in a short amount of time, the others take longer. So you no longer have a first-come, first-served situation. Instead, you may get last-come, first-served. The Core Fortran simply gets confused. You will get incorrect results. As a countermeasure, all request-response pairs needs to be serialized, implying a large performance hit. This is one thing that everyone wants to know. How fast is Julia in real-life usage, not in synthetic benchmarks? Julia folks have been making some extraordinary claims about beating Fortran. In my experience, at best, you could get about 100% the speed of C or Fortran. But in casual use, for example, hash tables, string concatenations, HTTP, WebSocket responses, well, typically you would get about half the speed of C or Fortran. One thing is certain, the development times are shorter. You simply get more productive in Julia, just as you do in Python. Let me give you a gaming analogy. I guess nobody would play an Xbox game at 30 frames per second. 60 FPS is the bare minimum. But what about 120 FPS? If 60 FPS is deemed sufficient, well, you may not necessarily need 120 FPS. At some point, running at half the speed of C or Fortran simply becomes sufficient, good enough. You may not even notice an extra delay of 1 millisecond or so. What are the reasons behind Julia falling behind C? Well, to start with, it's probably the usual suspect, garbage collection. Another thing that springs to mind is Julia's handling of half-float numbers. Julia does it always in software, or at least it used to. As you are aware, there are SIMD hardware instructions available on Intel and AMD CPUs. Julia can take full advantage of SIMD, but to get the most of the CPU, you still need to call an excellent Intel SPMD-C compiler, otherwise known as ISPC. This brings us to the next claim by Julia Fox about solving the so-called two-language problem. No, Julia does not solve it. It comes very close indeed, but doesn't solve it. So, why would anyone use Julia at all? Well, here's a single reason why the high-performance computing crowd might like Julia. Julia absolutely excels at distributed computing. It beats hands down MPI and coarrays. It is full asynchronous, and as you can see in this example, it's very much fire and forget. After launching the remote computation, you can do some other things and come back later on to collect the results. It's just so simple and it works. Unfortunately, not everything is great about Julia. There are still some rough edges. Here's a typical use scenario in high-performance computing. OpenMP is used alongside MPI. You use MPI across the cluster and OpenMP within each cluster node. Now you could certainly replicate it in Julia with base threads and the excellent distributed package. It will work fine in many cases, but it doesn't always work. The built-in base threads and distributed.jl simply do not get along very well at present. This might and, well, probably will change in the future. In the meantime, you can always try threads X instead of base threads and, well, see if your problems go away. We have come to the end of the talk. As ever, developers are faced with a familiar trade-off, development time versus execution speed. Handcrafted assembler is the absolute speed demon, but you know how long it takes to code in assembler. Julia's greatest strength lies in fast prototyping, whilst still offering decent execution speeds. And Julia is an undisputed champion when it comes to distributed computing. On the other hand, Julia still suffers from slow startup times. Each time you run your code, it needs to be compiled at runtime. Well, it is just like old petrol cars in the past, which needed a warm-up period in winter. And last of all, on a single server, Rust is not bad at all. So thank you very much for your attention. Any questions?
Thank you very much. And excellent timing as well. So I do believe that we have Christopher joining us through the online platform to ask some live questions. So there is one question that came in through the Discord platform, which is from Angus. I see you have WebGL support with HDR. I've been interested in this in Kata since we could benefit from 10 or 12-bit display output and a wider dynamic range. Was it easy enough to implement HDR, and do you require client-side calibration?
Well, basically, no, there's no client-side calibration. And the HDR part, well, it's handled in JavaScript. So it's handled within the client side, on the web browser, but there's no calibration at all. And I guess the Kata viewer uses the Electron framework, correct me if I'm wrong. So the Electron framework might be able to take advantage of the JavaScript, say, HDR capabilities. Well, to be exact, we use WebGL, and as long as the Electron framework can use WebGL, I think Kata should be okay with HDR.
Great, thank you so much. Are there any questions in the room? Okay, I see no questions, so in that case, thank you very much for a very interesting talk.
Thank you for your attention.
Thank you. And our last speaker for this session is Dino Bektasevic. It's also a recorded talk. I believe Dino will be able to answer questions on the Discord platform. And the title is Lessons Learned by Adding, sorry, I can't read my own handwriting. By adding cloud support to Ruben software. There we go.
Hello everyone, and thanks for coming to my talk. My name is Dino Bektasevic. I'm from University of Washington, Seattle, and I'm working with Andrew Connolly and the Ruben Data Management on adding support to Amazon Web Services to Ruben software. The next 12 minutes, I'm hoping to go quickly over the project, the way we did it, and talk a bit about the lessons I learned doing it. Rubin Observatory is an 8-meter telescope currently under construction in Chile, on which the legacy survey was based in time, while this LSSD Sky Survey will be conducted on. The 10-year Sky Survey will image the entire southern hemisphere every 3 nights, producing about 20 terabytes of data nightly. The end-delivered data volume is estimated to be between 300 and 500 petabytes. This data volume is kind of new to astronomy, so a lot of discussion and planning is happening regarding what data reduction pipelines need to look like and how will the user be given access to this data. The project itself would reduce the data in 3 locations, UK, France, and the US data facilities. Alongside processing the data, they would provide long-term storage and would provide data access to the end users. This would be achieved through the LSSD Science Platform. The Science Platform was designed as a set of services facilitating data access via portals, APIs, or explored through Jupyter Lab notebooks. To provide these services and resources for them, 10% of the Rubin compute resources are designated as shared user compute resources. The collaborative Jupyter Lab work environment that enables in-depth next-to-data analysis based around this idea of bringing analysis to the data instead of the other way around is what really caught our eye at UW. We began wondering if, instead of relying on the 10% allocated shared resources, could we also bring our own compute resources to the data? How useful would this be in enabling and or accelerating science, and how costly would it be to do something like this? The obvious implication here is that we don't want to purchase long-term standing hardware. We'd want to utilize cloud resources to achieve these goals to reduce costs. Cost comparisons between cloud and on-premise solutions are very difficult, but as a pure exercise in estimation, we can take 1 year Rubin on-premise deployment cost estimates and then compare them with the AWS calculator estimates. And we can see that while they're not very different, they do lean ever so slightly towards the cloud deployment. Unfortunately, the general consensus seems to be that in the long term, storage of large amounts of data in high availability data storage services is what drives the cost of cloud deployments. And there's no clear and easy way to estimate with certainty the point at which on-premise deployments would outperform cloud deployments in cost. But given the simple estimates above, and the fact that, let's say, if the 24 instances were procured all upfront standard reserved instances instead of on demand, the total estimate would stand at 285,000 United States dollars, right? The prospect starts to look quite attractive. We felt optimistic enough to move forward and add cloud support to Rubin Science Pipelines to see if we can improve on this simple cost estimate. The slide I'm showing a schematic representation of Rubin middleware component that ties the science pipelines being more on the right-hand side to the data I/O abstraction, the data butler on the left, right? The data butler is the abstraction that interfaces all data access and formats in Rubin middleware, making the science algorithms file system and file format agnostic. The butler does this by keeping tabs of the data types and locations in a database called a registry. And then when asked, it retrieves them from the data store. At the time of the development, this was just the POSIX file system. Right? The algorithms that are encapsulated in tasks can be chained into pipelines that are represented by directed acyclic graph, which makes this design able to execute very complicated workflows. To adopt the code to cloud services, we implemented S3 object storage functionality for the data store, and we added a PostgreSQL backend for the registry. At the time, they used SQLite for the development of the middleware component, and we wanted to use the AWS Relational Database Service to launch servers in AWS, so Postgres was a requirement for us. There's not a whole lot to say about the development experience here, except that it can be frustrating at times because of the sheer amount of services offered by AWS and the confusing ways in which they interact with each other. I would still say that majority of the core functionality was implemented relatively fast. This development wasn't a horrible experience. It's definitely personal opinion and not a general fact of the matter, because this was definitely helped along by the design choices made in middleware and the experience with AWS resources I had from previous similar projects that weren't as successful. Just keep that in mind, that there's an associated learning curve for each cloud provider. Had to pick a pet peeve, I would definitely pick how confusing the tooling can be. There's the management console, the CLI tools, which have 2 different versions now, the V1, installable by Conda, pip, and system package managers, and then the V2, the newer one, which has to be downloaded from a URL and seemingly contains an embedded copy of Python in the installer. The Boto 3 Python SDK is pretty great, but it has no official testing libraries. We use Moto, and that was a pretty pleasant experience, but it's important to note that Moto doesn't cover all of the AWS services to 100%. Boto 3 itself can be a bit confusing since similar functionality doesn't always do similar things like the example on the slide, so keep that in mind. Another thing to keep in mind is that S3 is not POSIX compliant file system. It will try to look like one though. Empty keys will be displayed and act like directories, but in reality, the mental model you want to adopt is more like a flat list of keys, right? So searching for matches has to search the whole list, but we don't have to do that, which can save on cost and performance. Little details like this can matter because, for example, if you scan a 20 terabyte data store just once a month, you'd pay about $10. But if this happens constantly in your code on 1,000 worker nodes, the end bill could measure in hundreds of dollars. And not to mention that this is costing in performance as well. Most of this, though, is not like an insurmountable problem, just kind of the reality of working with these systems. The end product, though, is the ability to run processing from any compute resource with the data persisted somewhere non-local, like S3 buckets. And since the AWS proof of concept was completed, the data management team added interfaces for Google Cloud Storage and WebDAV as well. What is missing from this picture is a way to scale up, some kind of a batching system and some kind of a resource procurement system. In our project, these roles were fulfilled in tandem by Pegasus Workflow Management System and HD Condor. To use Pegasus, we have to take the created science pipeline stack and then convert it to an abstract workflow, which is additional step, but this gives us more flexibility to adjust different parameters like CPU and memory requirements, clustering, staging, etc. right during this planning stage. The end product is an executable workflow, which is kind of just like a set of scripts that can be executed through HD Condor, like a regular scheduler. HD Condor also gives us HD Condor Annex, an additional tooling on top of HD Condor that provides the ability to provision compute instances with specified configuration and from specified Amazon Machine Images, AMIs. These instances can be dynamically added and removed from the compute pool, for example, when they idle for too long, which saves a lot of money. So in overview, this is kind of what the build system looks like. User would acquire a head node in which they would log in, and they would create a science pipeline workflow bag, which they would convert to an abstract workflow and submit to Pegasus. And if they needed, they could procure more compute resources using Condor Annex. In this proof of work concept, we built a system in which the user has complete control of the stack, which is both good and bad. It's good because the user gets absolutely complete control of any part of the system, but at the same time, it's also necessary for them to learn the tools, and there is a lot of friction there. There is a lot left to be said about integrating Pegasus and HD Condor with Jupyter notebooks, unfortunately, because they were never really intended to be used that way. However, the newer versions of these packages made great advances, making that possible. It's also possible to script out a lot of initial system configuration and resource creation, like the registry and the buckets, via Terraform scripts or Packer scripts, for example. This requires a bit of extra work and is external to these tools, which onboards kind of more and more maintenance to the developer. And that's another thing we learned. As we continued trying to develop and support this project with real users and real processing requirements, maintenance became a lot of work for a small team of me. Constant battle, between shared package version mismatches of Pegasus and Rubin, change of development direction from CentOS, changes to Rubin build system and HD Condor functionality. With so many moving parts, many of which are active developed in this area, the automation scripts and the deployed infrastructure requires constant adjustments. A fair question also here to ask here is, who also gets charged for all these resources and how do you control the limits? AWS uses a very powerful user identification and authentication system, but it's also kind of leaky. It can limit access to users to some services, regions, or instance times, but for example, it cannot limit the maximum number of instances users are allowed to launch or the maximum volume of EBS drives that are attached to those instances. I'm not really sure even now what the proper solution would be, but perhaps a more reactive approach is one of the options. Monitoring CloudTrail and AWS config logs to delete the resources that cross the limit is a way to go, but that is also a lot of tooling. Different architectures can help us out here as well. If we do not allow users to complete control of the hardware resources, we can use HD Condor UID domains to control the amount of resources as well as what resources users can access, which is great. But who is the person that controls and maintains the system then? And more to the point, these solutions seem to becoming more and more complicated. Perhaps answer already exists, we're just not aware of it. I believe data management teams are looking to Pandas Workflow Manager. Pandas is a tool of choice for the high energy physics community, which has been experimenting with cloud much longer, at least since 2017. So a lot of functionality could already be implemented. I want to point out that a lot of these solutions that discussed so far also don't really try to separate ourselves from the service provider specific tools like IAMs and AMIs, right? Containerization could be an answer to that problem because HD-Container can launch containers as jobs, but the problem can also be that these containers become very large. Stack install is typically 10 to 15 gigabytes alone. And there are other issues as well. And overall, there's just still plenty of work and ideas to explore in this area. And probably the slide everybody wanted to see is cost estimates. The details of estimated costs and workflows used to estimate them are best explained in more detail in the reference paper at the bottom of the slide, because they come with error bars and caveats and definitely could benefit from more work. The basic gist is that we estimate total data release production runs to be order of 0.9 million United States dollars on premise for 1 year, and in $0.7 million in cloud. Of course, these do not account for new optimizations like caching and decentralizing registry access patterns implemented since then, which do bring the cost even further down. Egress and storage costs still remain substantially large for large data sets. I think one of the important lessons that we also learned here is that if you can do the same work in 1/10 of a time on 10 times as many resources, you won't have to pay more. You'll pay the same price because that's how costing scales in cloud. It doesn't matter if you get results in a day or in 10 days, it costs the same, which brings about a different philosophical question, and that's at what point does enabling and accelerating science, shareability of the data, and risk mitigation aspects of using cloud resources surpass the monetary cost of cloud? A bit of too optimistic future perspective here might be that there's still many things that could reduce our cost footprint in the cloud that could be implemented. Tier storage would allow us to amortize those costs. New services like Cloudflare Object Storage supposedly won't charge egress costs. Long-term standing contracts would be a good thing, right? So there's still plenty to explore there as well. In the interest of time, I won't repeat all the points made here, but in short, containerization is likely the way to go. More optimizations are possible. Extending the cloud deployment remains cost-effective if we can implement those. Rubin has recognized these facts, and they've tendered contract to Google Cloud to develop and deploy the intermediate data facility for the first 3 years of the LSST project. If these are topics that you're interested in, I would definitely recommend paying closer attention to the Link Framework project, which is a collaboration between University of Washington, LSST Corporation, and Carnegie Mellon University, as they will be attempting to solve exactly these issues. And they will be hiring soon, I hope. I think that's all I really have to say. Thanks for listening. Apologies for walls of texts. I can take questions now.
Thank you for that. There's one question that come into Discord. Could you comment on any specific lessons learned from DP0 as you have actual users trying out the platform? This is from Michelle.
Yeah, thanks for the question, Michelle. Unfortunately, I'm not, DP0 and the IDF facility is on a Rubin side, and I'm not personally involved in the deployment of the DP0 on IDF, so I would not know much about that. What I do know is that they would host notebooks and data, but I don't believe that there would be a batching system for large-scale processing involved in DP0 at the moment. I see you already gotten your answers in the chat there.
Thank you. I see there's also other answers coming in through Discord. Would anyone in the room like to ask a question? Okay, so it seems like the conversations will continue online. So I see that in your conclusions you mentioned that they'll be hiring soon. So I want to just highlight to everyone in the room and online that there's a job board channel associated with the Discord platform where any positions can be advertised. So thank you very much again for this great talk. And just as we go into our break, I would just like to mention to the online participants that the poster lightning talks, the quick little videos for posters will be played on the virtual stage on the website, the same place as you watch this video. and we will reconvene at 12 o'clock local time. Thank you very much. And thanks again to all the speakers.
C++ language. Several libraries already existed to read and write FITS files in C++. Yet, none of them provided the type safety we'd expected. Therefore, we have internally developed LFITS, which is both safer and easier to use. It is also as fast as CFITS.io, not to say faster in some circumstances. As an example, here is how to create a single image FITS file with one keyword record using CFITS.io. Now, using CCFITS, and finally LFITS. More compact code with less parameters means less development errors. On performance side, LFITS is equivalent to CFITS.io. Yet, internal optimizations for tables dramatically reduce runtimes as compared to the classical usage of CFITS.io. Come join us at the poster sessions and have a look at the library on GitHub.
My name is David Keiderling. I'm from the Max Planck Institute for Solar System Research in Göttingen. We are a main contributor to the Science Ground segment of the European Planet Detection Mission Plato. I want to bring to your attention my poster with the title Distributed Development of the Level 1 Data Processing for the Science Ground segment of the ESA Plato mission. In this poster, I introduce some key aspects of our development and how we create science-ready data products for the Plato Science Ground segment. I would like to invite you to have a look at the poster, discuss it with me, and exchange some experience. See you at the posters. Thank you very much.
My name is Marcos López Caniego. I'm an astronomer working at the ISAC Science Data Center. I'm going to tell you about the James Webb area of ESA Data Labs. ESA Data Labs is a science exploitation platform sitting on top of the astronomy archives at ISAC. And when it becomes publicly available in a few months' time, users of Webb will have a place to come and explore and analyze data. Our platform is based on Docker containers and JupyterLab, but it also works with Jupyter Notebooks. So the users of Webb, they will also have access to PySky, our JupyterLab widget for ESA Sky, and that includes the James Webb planning tool to help prepare future observations. And it also includes several example notebooks to show users how to explore our archive, and also how to analyze data using the STSCI provided data analysis notebooks. So we hope you like the poster, and please do not hesitate contacting us. Thank you.
Hi, my name is John Swinwick. I work at Astron, the Netherlands Institute for Radio Astronomy, and I'm the coordinator of the ESCAPE project's Work Package 5. ESCAPE is a major European project putting together solutions for data-intensive astronomy and particle physics. We're developing data lakes for dealing with massive data volumes, cutting-edge scientific software repositories, deep integration with the virtual observatory, and gateways to citizen science projects. You can learn more about all of these across this conference. Here, though, I'd like to draw your attention to ESAP, the ESCAPE platform. ESAP is our effort to put together not a single science platform, but a toolkit that you can use to build and customize a science platform for your specific project or application. I hope you'll check out our poster, and I hope you'll find ESAP useful in your own work. You can see my email address at the side of the screen, and I'd love to hear from you with any comments and questions, and I hope you'll enjoy the rest of the conference. Goodbye.
Hi, my name is Anastasia Alexa, and my poster's on the struggles to find a good electronic document management system for the DKIST project. The DKIST project does have a document management system, but we wanted to find a different system with lower cost, less complex, more modern, and with easier workflows for over 1 million documents and 500,000 different folders. We tried over 20 different products that were either too expensive, difficult to manage, or were not recommended. And we came up with Box and Box Relay. It was by far the best product that we had tested. It's similar to Dropbox. It has native workflows. It has native approvals and native signatures. It's modern. It's cloud-based. It's FedRAMP compliant. That means it has high security. And you can put your 99 and ITAR data in Box. It requires minimal administration. It has workflow histories. We found it by far to be the best product out there. And we hope that you find this investigation useful to possibly replace your electronic document management system, which I know a lot of you have been struggling with yourselves. Thank you very much.
I'd like to talk how to use computing and data science to accelerate knowledge discovery in astronomy, where I focus on automated spectroscopic analysis of X-ray data. The methods described here are also valuable for many applications that have a large data set. Genetic algorithm is a class of heuristic method inspired by the theory of evolution, using selection, crossover, mutation to find optimized solution. We applied the GA method to a starburst galaxy NGC 253. Manual fitting and automated GA fitting match quite well in a wide range when the same physics models are selected. However, our GA code only requires a few minutes running without human intervention, making it itself a high-performance method to leverage the information collected through instruments. Thank you.
In order to address astronomical data in its big scale and variety, we propose a web application that helps researchers to explore datasets with the help of machine learning. UltraPing performs dimensionality reduction by training a self-organizing coordinate map, SOM in short, and allows you to organize, inspect, and interact with these maps. Visit a SOM and you'll see a topology of generated images, prototypes representing the most common shapes in your dataset. You can select individual prototypes or multiple at once. Change between multiple views, like one that shows you an overview among the given labels. The heat map view informs you about how many data points from your set match best to a prototype. For each prototype, you can request the best matching data points. The data points themselves can be inspected in an individual page with a LED-in light. Key feature of UltraPing is the abstract design pattern of its function set, which is continuously growing with the goal to create the ultimate explorer's toolbox for you data jungle adventurers.
Hello, we are going to introduce you to our project PyCF3. PyCF3 is a Python library that integrates the web service of CosmicFlow's 3-distance velocity calculator with the Python scientific stack. It pursues two main objectives: to accelerate local computation times, and to not overload the server with repeated calculations. For example, if we instantiate a connection to the CF3 calculator and perform the same distance calculation twice, the second call accesses a local cache, accelerating the process to approximately 2 or 3 microseconds. The results has all the attributes that are available in the web version, and they can be accessed as a NumPy array, as well as the raw result in JSON format. Finally, the project follows a strict quality standard and has detailed documentation. If you have any questions, please do not hesitate to contact us or visit the project website. Thank you.
So hello everyone, my name is Jakub Jurisek and I'm from University of Geneva, and I would like to invite you to check our poster on reconstruction of data from LST-1 telescope using convolutional neural networks. With imaging atmospheric telescopes, we observe atmospheric showers of secondary particles, which are produced by primary very high energy particles or gamma ray photons. If we analyze the images, we can separate the gamma rays from hadronic cosmic ray background, reconstruct energy of the gamma ray photon and its arrival direction. In our analysis, we use modified inception architecture to analyze the images from LST-1 telescope, which is a prototype for the Cherenkov Telescope Array Observatory, and show that the reconstruction performance of this method has a potential to beat classic method of reconstruction like random forests.
Hi everyone, thank you for the opportunity to present our work. Today we will be showing a new form of machine learning architecture known as the transformer architecture to detect strong gravitational lenses. Currently, the most common method for finding strong gravitational lenses is using convolutional neural networks. From the data from the Bologna lens challenge, we were able to show that the transformer architecture can perform better than the convolutional neural networks in every category and also has better stability compared to CNNs. The results from our study are given in this poster.
Hello to everyone. In this short talk, I will present you the preliminary results that we obtained with a deep learning anomaly detection method developed to identify gamma ray paths in the data acquired by the Agile satellite. This anomaly detection method aims to detect GRBs in the multivariate time series acquired by the 5 panels of the Agile anti-coincidence system. We implemented the model with a convolutional neural network autoencoder. We trained the model with an unsupervised learning process using 5,000 background-only multivariate time series. The preliminary results obtained with this training model prove the ability of this method to detect the GRBs in the Agile anti-coincidence data. This model can be implemented into the Agile automated real-time analysis pipeline to improve the GRBs detection capability.
Hi everybody, my name is Simone Riggi, I work at INAF in Italy, and in this short video I would like to briefly summarize our ADAS contribution. As you might know, the Square Kilometre Array will be the largest and most sensitive telescope ever built. One of the major challenges will be dealing with the huge amount of data that will be produced and extracting signs from them in a mostly automated and reproducible way. For that reason, we have started a new project called CIRASA, which aims to develop a visual analytic platform by integrating different services for visualization, archiving, and source extraction. So far for the project, we have developed a new source extraction service, which currently integrates and supports multiple source finding applications, from traditional ones to novel applications based on deep learning techniques. We are currently deploying these services on a prototype European Open Science Cloud infrastructure, so to make them available to end users. You can find more details in the poster and in forthcoming papers, and you can write to me for questions or requests for collaboration at simone.riggi@inaf.it.
Hi, I'm Julien Plante, and thanks for watching my lightning talk about a novel fast radio burst detection pipeline for Nenifar. So, in a nutshell, this pipeline is about detecting fast radio bursts in real time to trigger the storage of the time frequency signal. This avoids filling entire hard drives with the data containing little to no events. We also needed this pipeline because of the great dispersive delays faced at Nenifar, which are about 1,000 times greater than for usual radio telescopes. Apart from the pipeline itself, here are the main contributions. So we have a new approach illustrated by the animation below to the dispersion visual transform, and coming on top of existing implementations such as brute force DMT or fast DMT. We also use GPU Direct for data acquisition and a new image processing approach to pulse detection that we find promising. So if you have any question, feel free to join my gather.town.
Hello, I am Federico Incardona. I would like to invite you to take a look at my poster, which is number X2002, in which we present some preliminary test results for the correct sizing of the hardware that we lost the database for the monitoring system of the Cherenkov Telescope Array, CTA. The MON is the subsystem of the array control and data acquisition system that is responsible for monitoring and logging the overall CTA array. It acquires and stores monitoring points and logging information from the array elements at each of the CTA sites. MON is designed and built in order to deal with big data time series and exploit some of the currently most advanced technologies in the fields of database and Internet of Things. In this poster, we present the test campaign that we performed to dimension the bare metal hardware requirement, and we discuss the best set of parameters that maximize the database data writing.
Hello everyone, this is Javier Espinosa, software engineer working at Array Assistant for ESA, and I would like to invite you to see our poster about the design and development of modern science archives at the ESA Science Data Center. The key objectives of ESAC are the long-term preservation of the data coming from a wide variety of missions and the provision of access to scientists all around the world using as many entry points as possible. For this reason, our archives have been evolving since old Java web-style applications to our latest developments in Angular, and a common methodology has been defined to ensure good practices, for example, reusability across missions, maintainability, and testing. We will also show you the benefits of choosing Angular through some examples of the amazing new features we have already implemented in our science archives, such as our data and image viewers for different sources, our ESA Sky fully integrated in Angular, and of course, improvements in user experience. Come and visit us.
Hello everyone, and thank you for viewing my presentation. My name is Anthony Hang. I am a software developer for the Australian Astronomical Optics, working with the European Southern Observatory to introduce the PyCPL project. So, the goal of this project is to provide access to ESA's common pipeline library held within the Python environment. Originally, CPL was used for the construction of standardized data reduction pipelines in C. However, as Python is becoming more used for data processing over C and C++, there can be a need to build a Pythonic object-oriented interface to CPL. This enables existing CPL developers to rapidly prototype new pipelines, and allows Python developers within the astronomical community to utilize the CPL toolset. So, our poster will go over the general structure of the bindings from CPL to the Python environment, using a combination of C++ and Python 11. We also detail some of the challenges we faced through the process of connecting the various layers together. Our project is currently in beta with most CPL structures and functions already bound, as well as support for executing existing CPL pipelines and building new Python pipelines. Plans have been made to begin using PyCPL to prototype new pipelines for Mavis. So, thank you for listening. If you'd like to know more about this project, feel free to visit our poster and discuss with us on Discord.
Hello, I am Eva Sciacca from the Italian National Institute for Astrophysics, and I am pleased to introduce our work related to the onboarding of space services to the European Open Science Cloud. The NIENIS project is implementing novel thematic services addressing emerging challenges in underwater, atmospheric, and space sciences to be delivered to the European Open Science Cloud, EOSC. We report on the current development status of services for the astrophysics and the planetary communities, focusing on visualizing and data management, SpaceVis, map making and mosaicing, SpaceMOS, and structure detection with machine learning, SpaceML. We present the challenges in maturing the technological solutions to TRL8 in order to obtain robust delivered cloud services within the emerging EOSC. Thank you for listening, and we look forward for your feedback on the latest release of the NIENIS space services.
The NASA Astronomical Virtual Observatory have been developing tutorials and giving workshops to show astronomers how to find and retrieve the data they need in Python, and without having to know which archive has it and how to use that archive's custom interface. This will be increasingly important as multi-wavelength and multi-messenger astronomy expands, and as programmatic data access for computationally expensive analysis becomes more necessary. The virtual observatory is used in many invisible ways across many archives around the world, and underlies, for example, many functions of the popular AstroQuery package. But another AstroPy-affiliated package called PyVO is a way to find and access these data without needing to know which archive's website and which AstroQuery module you need. In this poster, we present an overview of what these workshops do and why, and give links to the online materials that we hope will be more broadly useful to the community.
Hello, my name is Stéphane Erard. I'm an observer at the Observatory of Paris, and I'm in charge of the VESPA activity in the Europlanet program. VESPA is about providing access to solar system data and planetary science data in general, using a system which relies on virtual observatory standards. In the poster we present at this conference, we're using this VESPA infrastructure to provide access to a selection of data catalogs distributed in the Vizier system. So Vizier is a set of astronomical catalogs related to publications, from which we extracted only the ones related to the solar system. And this service is responsive to the ePNTAP access protocol, which is currently a proposed recommendation at IVOA. Thanks for attention.
Okay, that's it for the first poster session. Thank you, everyone. We'll see you again at 12 o'clock. The second half of posters will be broadcast later in the second poster session. Thank you. Okay, let's go. Okay, good afternoon now. It's 12 o'clock for our last session before the long lunch break. So the first speaker in this session is Michelle Lochner, who is going to tell us about anomaly detection in astronomical data using machine learning.
Awesome. Thanks, Carolina. Hi, everybody. It's amazing to be here at a real conference with real human beings instead of speaking to a blank screen. So thank you so much to the organizers for inviting me. So I'm Michelle Lochner. I'm a senior lecturer at the University of the Western Cape, and I also have a staff scientist position at the South African Radio Astronomy Observatory. And I'm going to be talking about anomaly detection in general, so it's not specific to radio astronomy, although it will feature. And I just wanted to highlight that this is work done in collaboration with lots of great people who I've listed there at the front. This is very difficult for me because I like to pace when I talk, so I'm having to force myself to stand in one place. Okay, so I want to set the stage for why we're trying to do what we're doing. And the first place, I want to basically mention two very exciting telescopes. The first you've heard about already today, the Vera C. Rubin Observatory under construction in Chile, which is going to run its 10-year legacy survey of space and time. And this telescope is really amazing because it's got clever optics, it's got the world's biggest camera, and what it means is that it's got a big field of view, it can go very deep, and it can do this very quickly. So it can essentially make a movie of a big chunk of the southern sky. And so this is an animation of supernova discoveries, so how many supernovae the Rubin will detect. But what's cooler than this, what's a nice bigger number, is to think about the total number of transients that Rubin will detect. Every single night, 10 million times a night, something is going to change. And Rubin will issue an alert. So that's 10 million alerts every single night. And about half of those are actually real astronomical events. So when you talk about velocity, this is really what we mean. On the other side of the spectrum, we've also heard about, and this is something I think near and dear to almost all of our hearts, is the square kilometer array. So this is in the works a few years down the line. This will be the biggest telescope in the world. And we're also facing an unbelievable data rates challenge. Obviously, we all know about the incredible raw data rates, which Rob mentioned this morning. But even the processed data, even after you've done all the hard work of producing images and catalogs, we're going to have like 1 billion galaxies to look through. And for many of us who've done a lot of radio astronomy, we're kind of used to this whole being able to download stuff into your laptop and fiddle around with it, whatever. And we've heard a lot of talks already about how that's just not possible. And we really have to change our ways and deal with the size of these data sets. And of course, the future's already here because we have the precursor arrays. So we've got Meerkat in South Africa, we've got ASCAP in Australia, and we've got LOFAR in Europe, and these are already kind of pushing the boundaries in terms of data quantity. So essentially, I wanted to start this talk by reminding us that we are facing a data explosion. And what are we going to do about it? And of course, many of us are quite sold on the idea of using machine learning to try and help automate as much as possible. So this talk is about anomaly detection. And I think we all kind of have an intrinsic idea of what an anomaly is. It's anything that's different, anything that's unusual, that's not similar to the majority of the data set. And now we could split these up into kind of known unknowns. So these are objects that are rare, but we know about them. So an example, for instance, is strong lensing in the optical, or gravitational waves. These are rare events, but because we know about them, we may not be able to build training sets to look for them, but we kind of know they're out there and we know how to look for them. They are still very much anomalies, though. But of course, what we're all excited about is the unknown unknowns, the true scientific discoveries, the things that nobody was expecting. And this is what's really exciting when you start to go to enormous data volumes. And I like the example of the pulsar because in 1967, it took a very bright graduate student named Jocelyn Bell Burnell to manually go through all her data and notice something weird. So, and I think most big astronomical discoveries are made in this kind of way. It takes a human looking at the data, noticing something strange, and then following up on it. So the question is, how are we going to discover genuinely new phenomena when there's 10 million alerts a night? When there's 1 billion galaxies in your data set? How do we automate the process of discovery? And this is where anomaly detection can play a critical role. So I'm not going to go into a whole background of machine learning and how it works, especially because this is a branch of machine learning you don't often hear about, although you have already heard one really great talk on it this morning, which is unsupervised learning. So you don't have labeled data. This is different from the is it a cat or is it a dog example, because we are, by definition, looking for things that we don't know what they look like. So there are a bunch of machine learning algorithms that are designed to operate in this kind of regime. And more or less, they just take the data set, try to figure out what the kind of majority looks like, and identify things that are quite different from those. So 2 very simple examples. I'm not going to go into details, but on the left there you can see isolation forests, which is an algorithm based on a very popular random forest algorithm. And it basically tries to split up the data to try and isolate each point, with the idea being that points that are near lots of other points are hard to isolate. Points that are far away are easy to isolate. So it's a pretty simple algorithm, but actually extremely effective for anomaly detection. And on the right there, I've got local outlier factor, which is a density-based algorithm, simply looking for anything in a low-density regime. I've worked on a few other anomaly detection algorithms, some novel anomaly detection algorithms in the past. I'm particularly fond of BADAC, which is the Bayesian anomaly detection and classification algorithm. What's nice about this is it takes into account uncertainties, which, because machine learning is a field driven by industry, is not common. Most machine learning algorithms are not uncertainty aware and don't take this into account. So BADAC is really nice, especially if you're in the kind of low signal to noise regime. And then on the right, there's another algorithm developed by my collaborators called DRAMA, which is a deep learning-based algorithm. Effectively uses deep learning to reduce your data down to a latent space and do anomaly detection in that space where it's a bit easier. So that's also a very nice algorithm, and all the papers are there if you want to check them out. So the key thing that I wanted to talk about here, though, is when Bruce Bassett, my collaborator, and I were originally talking about anomaly detection, wanting to work on this problem, we kind of early on realized anomaly detection alone is not enough, especially if you've got 10 million alerts a night. Just finding that you may end up with 2,000 anomalies to look through. So there has to be another step after the anomaly detection. And what's interesting is that this step is subjective. And that's different from like a spiral versus an elliptical galaxy. We can all agree on that kind of classification scheme. But while many things can be anomalies, not all of them are going to be interesting to you as a scientist. So for example, on the screen, I've got artifacts on the left, which you as an astronomer probably would want to get rid of. And I would be more interested in the real sources on the right. But if you're interested in checking your data quality, for example, you care about the artifacts. You want to know about them. So there's this intrinsic subjectiveness to the second stage, which is, are these anomalies interesting to you or not? And so you need a kind of, almost like a recommendation engine. So something that is able to operate in an unsupervised way, so without much training data, to be able to recommend to you the kinds of anomalies that you might be interested in. And this is a branch of machine learning called active learning. And that is where you combine the raw processing power of the machine learning algorithm with the human intuition, creativity, and expert knowledge. And what I'm really interested in is how because my experience with machine learning has made it abundantly clear that we can't really just trust these algorithms to just carry on their own. There has to be a human involved in these final decision-making processes. So the key question is, how do we best leverage the machine learning algorithm to free up as much expert time as possible and use that expert time wisely? And our attempted response to this is called astronomaly. So this is a very general purpose anomaly detection framework for astronomical data. And you can see on the left there, it starts with what is really a pretty standard machine learning pipeline. It starts with reading in the data. It can work for image data, be it optical, radio, whatever. It can work for time series data. It can work for spectra, features, etc. With the caveat, of course, that there are many data formats. So it may require some slight tweaking, but in theory, it can work with basically anything. The next step is extremely important, and it's called feature extraction. And that is where you reduce your data down into something simpler that best represents your data. And we saw a really good example of that this morning in Fernando's talk, where you use an autoencoder to bring, and you can use those as a feature extractor to bring your complicated data down to a simpler set of numbers. And the way you do that is very important, and it will dictate the types of anomalies that you end up being sensitive to. The next step is anomaly detection, and I have a couple of standard anomaly detection algorithms, including a couple that I showed you earlier. But the part after that is what's really critical. So up until now, it's just some Python code running in the background, doing this machine learning. The important step is the active learning, bringing in the human part of this algorithm. And you can see in the screenshot on the right is the JavaScript interface that I built, which allows you to very easily go through your data, label it, and when I say label, I'm not talking about labeling 100,000 examples, I'm talking about labeling maybe like 50 or 100, which only takes a couple of minutes with this interface. But you're basically just telling the algorithm, you're not saying, yes, this is this type of galaxy, or this is whatever other type of galaxy. You're just saying, I'm interested in this. I want to see more of this. And then we built a novel and active learning approach that will improve your anomaly detection and show you more of the things that you like and less of the things like maybe artifacts, for example, that you don't like. And one key point to make here is that within this active learning approach, we included an idea of kind of uncertainty. So if there's a regime in which there is not much labeled data and the algorithm's not really sure, and it finds something anomalous, you're going to see it. So you're not going to miss anything, but you are going to spend less time on the junk that you maybe don't care about. So the code is available. The link is at the bottom. I would be absolutely delighted if you wanted to try this out on your data. It's, of course, still very much in development, so send me a message when you inevitably get stuck with something. And the paper is out at the bottom. OK, so let's actually see this in action. So with this data set that I'm working with, this is from the Galaxy Zoo, which is a citizen science project, lots of labeled data, including some objects that were labeled as odd. It's not very specific, but it's odd. And if you look at if I take the data and just order it randomly, you mostly see like ellipticals, spirals, kind of boring galaxies. I now run my machine learning algorithm with a fairly simple feature extractor that I built. And I've sorted the data from most to least anomalous. So remember, at no point have I told this explicitly what I'm looking for. This is just what the machine learning algorithm thinks is weird. And I can now go through this data very, very quickly and evaluate each of these objects. So you'll see at the bottom of the screen the numbers are changing. That's because for some things it's like an artifact, or it's something that is maybe just coincidental galaxies or whatever. So I'm telling it how interested I am in each of these. I then run the active learning algorithm and order it again from most to least interesting, but now by the new score. And you see it does a pretty good job of getting rid of the artifacts and just prioritizing the things that I, as a user, care about. So really the whole idea is to massively speed up the amount of time that we need to spend looking through the data to find things that are interesting and worth pursuing. This is just to visualize what's actually happening in the algorithm. This is quite hard to do without a pointer, but what you're seeing on the left is the raw anomaly score, just a map of it in some representation of the data space. And on the right is after it's been retrained. So basically, regions where I've ranked objects very highly is very interesting, kind of get upweighted. And regions that I've ranked very low get downweighted. So that's kind of the simple idea. OK, I'd be completely remiss to not show some Meerkat data. So this is the MGCLS dataset, the same one that Fernando mentioned this morning. And again, I've just started it with a random sampling. So you're mostly just seeing ordinary sources from PyBDSF. When I run this, exactly the same algorithm that I ran with the optical data, which is kind of cool. I didn't have to laboriously retrain anything. I could just run exactly the same approach and order things from, again, most to least anomalous. You can see it is definitely picking out stuff that's different from the norm. Mostly anything with kind of weird morphology gets picked out. And here's a little wallpaper of, I think these are the top 10 anomalies. So I wasn't as patient as Fernando was, so everything is automated. I haven't manually looked through the data, really, so that you do occasionally see repeated sources. But other than that, it does a reasonable job at very quickly showing you stuff to see if there's anything interesting that you want to look at. Okay. Oh yes, and then one more application, which I can't help show just because they're really pretty. And this is the Decals survey. So this is a massive optical survey that's very recently been done. My master's student has been looking at applying astronomy to this data. And as always is the case with machine learning, whenever you go from a nicely curated data set to something more realistic, everything falls down. So he spent a lot of time working on improving the algorithm to get it to operate with more kind of raw data, because the Galaxy Zoo data is really beautiful and curated and easy. So I wanted to show you some examples with time series data as well. So this is all exactly, this is the cool thing with the algorithm, is that after you've done the feature extraction, everything else stays the same. So working with transient data, for example, was fine. There wasn't any problem. So I have another student working on looking at anomalous transients in the CRTS data and finding a couple of weird carbon stars, flare stars, etc. But one thing I really wanted to talk about is this application, because I think this could actually be a model for the types of analyses that we can do, especially for something like Meerkat, because Meerkat is really pushing the boundaries of sensitivity. So it's finding things that we have never really seen before. And the problem with trying to apply standard supervised learning approaches is that we just don't have the training data. So an unsupervised approach is definitely going to be more effective, I think. But it's critical that you include that active learning component. Otherwise, the algorithms are fairly useless. So here's a cool example of this. So this is a bright student. She's now a postdoc in Australia, Sarah Webb. And she came to me with this data set of 1 million light curves taken from the Deeper, Wider, Faster program. So this is a cool program where they're trying to detect fast transients, so things on like the minute time scale. And this is a regime that hasn't really been probed much in astronomy. So we kind of expect to find things that we haven't really seen before. But she had this big data set, nobody had looked at it, it didn't have any labels, and it was just enormous. And so what she did was she took one field, which was still about 80,000 light curves, and we used a fairly standard feature extraction package. And the key thing is that she applied clustering. So this is an algorithm called HDB scan, which automatically tries to collect together similar objects, basically, so similar in feature space. And when she used HDB scan, she found these big clusters, and some of them, she could basically throw away huge chunks of the data just by looking at a few examples from that cluster. So, oh, these are all artifacts caused by this thing. Oh, these are all just standard stars. We can just throw them away. So she can get through 80,000 light curves, with minimal amount of human intervention time. And that let her focus on the things that were actually important. So she took kind of the remaining data, things that don't fit into clusters, and ran astronomy on it. And it worked pretty well. So she was able to pick out a few known variable stars and make some new discoveries, and also discovers some weirdly behaving flare star. So this was just an example of taking a data set, completely unlabeled, not very much known about it, to actually getting some science results using unsupervised learning. So I do think that this could be a model that we could use going forward. Then this is a nice example, and actually this is an example of where machine learning doesn't work very well. So I think quite often when we give these machine learning talks, we're always like, oh, it's amazing, it solves everything, but actually in reality, there's some problems where it's not the right tool for the job. So the problem here is when Rubin is going to make these 10 million alerts every single night, we need to know if there's anything interesting that we want to follow up. But we need to know in real time. So this is much harder than taking a known data set of light curves and classifying them, for example. We have to be able to do this in real time. So I had this very simple idea of if we had a model for what we expect a particular object to look like a type 1a supernova, and we detect a point that deviates from the model, well, that might be an anomaly. And so this was the idea that Dan Muthukrishna, who's now a postdoc at MIT, worked on. So what you're seeing is a deep learning model using a temporal CNN, making predictions based on previous points in the light curve. And it does a reasonably good job. The problem is that it actually does too good a job. And the deep learning algorithm was too flexible. It was able to basically fit anything. So these are very complicated plots. Don't worry too much. Basically, what you want is for the left part of it to look, the left part of this matrix to look very blue, and the right part to look very red. That means it's detecting anomalies. And the deep learning algorithm didn't really work that well. What worked much better is a good old-fashioned Bayesian statistics approach, where we used a parametric model, we fit it, and we were able to detect anomalies that way. So this paper should be on the archive in the next week or two. The final application I wanted to mention, because this is something I'm very excited about. So this was a very bright postdoc at Manchester. It's great to work with young people who see what you do and then take a look at it and go, oh, I think I could do that better. And they're not completely right. So he, instead of using my very simple features that I use for morphology, he had a trained CNN based on Galaxy Zoo data and used those latent features as features for anomaly detection. And you can just see in the plot on the left that he does massively better. And this is with the CNN trained on a different data set and applied to SDSS. So the idea is that by solving a classification problem, you produce a useful feature extractor for other problems. And although we don't have yet this kind of training data in radio astronomy, I think the idea of representation learning could be really a powerful approach. Okay, so I wanted to finish off. I think I've got 2 minutes left or so, and now that I have all of your undivided attention, I'm going to shamelessly advertise. The first thing I wanted to advertise is the Supernova Foundation, which is a mentoring program, an international mentoring program that I run for women and gender minorities in physics. So here's a screenshot of some of our lovely mentors. So we are always looking for new mentors and mentees, so if you're interested, please check out the website. And finally, I wanted to advertise a postdoc. If anyone's interested in coming working with me, it starts next year. And it's fairly flexible, anything related to Rubin, vaguely related to Rubin or multi-wavelength stuff, and preferably to do with machine learning. It can be difficult to compete with, some of the more well-known universities in the world, so I thought the most sensible thing to do is to just show pictures of Cape Town. And this is an unbiased representative training set, because these are pictures that I took myself. So if you're interested, please send me an email and check out the website. And of course, you can just send me a message on Discord. And I'm going to finish off with just a couple of conclusions. Basically, machine learning is pretty critical. It's not something that can just be used out of the box for absolutely everything to solve every problem. But there are many problems, like dealing with the 10 million alerts a night, that we just can't really do without machine learning. But I think that we need to really start pushing it to its limits and try to automate things. Well, I mean, not fully automate anomaly detection, but automate a lot of the hard work so that we can make really good use of the expert time. And our attempt at this is Astronomaly, which you can check out there. And of course, I'm just going to add these links to the Supernova Foundation and a reminder about the postdoc. And I think I'm exactly on time. Thank you very much.
Thank you very much, Michelle. We have some questions that have come in. One question from Specicle, who says, have you considered using more than morphology when searching for interesting sources, for example, spectrum?
Yeah, definitely. Astronomy is a framework, and it's very modular, so you can kind of put anything you want in. And at the end of the day, you give the algorithm whatever features you think are a sensible representation of your data. So if you have additional information, like redshift or spectroscopic information or whatever, then you can just add those as features. And it's really important because, like, for example, the Galaxy Zoo example that I showed, the features that I used are just sensitive to morphology. And even then, they're not great. Like that CNN that Mike built is much better. But if anything came up that was a weird color, my features wouldn't pick up on it. So your choice of features is really important. And it does mean, we do have to know a little bit about the data. Even if we don't necessarily know what we're looking for, we may know that, okay, anomalies can be weird in a number of different ways, like morphology, color, spectra, etc. So short answer is yes, you can add anything. But in the first initial paper, we mostly just use morphology.
Okay, thank you. And we have another question here from Ben, so if you could please walk to the microphone.
That was an excellent talk. Just a quick question. You mentioned artifact detection in passing. Has there been any progress in using this anomaly detection tool of yours to auto-tag and detect places where direction-dependent calibration can be applied? Because we now have all the tools to do the direction-dependent calibration peeling, but tools to actually detect where those should be peeled is not quite there yet, and not automated.
That's a good idea, yeah. Actually, Spey and I were chatting in passing with something similar. So it's not something I've attempted yet, but in playing with like the MGCLS data, for instance, or a different data set which had much worse DDE effects, it became quite obvious that these artifacts do get flagged as anomalies. And so if that is what you're looking for, then yeah, for sure, you can just flag them and find those kind of areas. But I think I would want to use a better feature extractor than what I'm currently using. So for something like that, where you're just trying to detect that kind of structure, just the PSD, which is one of the feature extractors I have, might actually work well enough for that. So yeah, it's definitely something you could do.
All right,
we should chat about it.
Cool.
Great, excellent. We have no more direct questions in the Discord. I don't know if there are more questions in the room. No? Okay, then thank you so much, Michelle, for this great talk. And our next speaker is Victoria Topton, homogenization of multi-wavelength photometric data for RCSE DV2.
Hello, and thank you. Hello, my name is Victoria Toptun. I'm working in SciMSU in Moscow, and today I will talk about homogenization of multivalent photometric data for RCSD-V2. What is RCSD? RCSD stands for the Reference Catalog of Spectral Energy Distributions. This is our project that contains multivalent data for 900,000 galaxies from SDSS DR7. And for all of them, it contains photometry from SDSS, UKITS, and GALAX. Our motivation was to create a catalog of SDSS spectra that contains homogeneous analysis of all of them, their absorption and emission line properties, and also multivalent photometry. A lot of scientific research have already been done on the basis of RCSD. For example, now we are actively working on finding of intermediate mass black holes in the center of RCSD galaxies. And first work about it was published in 2018. Also this year will be published in Nature Astronomy work about progenitors of ultra-diffuse galaxies. And based on the first results of RCSD in 2015, in Science was published our work about finding of 11 isolated compact elliptical galaxies. So we would like to expand the catalog that turned out to be so practically useful. So here I present the RCSD V2. RCSD V2 is the second generation of RCSD that contains more than 5 and 6 million spectra. And at the slide you can see that our catalog covers all the sky and southern sky too. Also you can see the example of our website, and by this link you can learn more about the site. And also learn more about our project you can see at the Igor Chilingarian's poster. At the basis of RCSD is our sample of spectra from a lot of spectral catalogs. We selected only spectra from galaxies, so we selected spectra with redshifts more than 0.016 or redshifts less than this point, but matched with galaxies from Hyperleda. It is very important that our spectra all homogeneously fitted with n-burst spectral fitting algorithm. And on the slide you can see the example of the same spectra, but on the upper frame it fitted by absorption lines, and the lower frame it fitted by absorption and emission lines. More about a very important part of our project as spectral fitting you can learn from Vladimir Garajanov's poster. And let's talk about our main topic. It is photometric data for RCSD V2. We collected integrated photometry and aperture photometry for all of our sources. And this photometry comes from a lot of catalogs that cover all the spectral range, from near UV to mid-infrared. Also, our photometric catalog covers all the sky and southern sky too. All of the data was taken using publicly available virtual observatory services as CastJobs, NOAA Data Lab, etc. However, the main problem was not just to collect photometrical data, but to calibrate it so the data from different surveys coincided with each other. And let's talk about this calibration. Firstly, we consider galactic dust reddening using EB-V from Shalev-Lengfing-Byram extinction maps. Also, we calculated extinction using coefficient that different for every filter, and we took that from literature. So we have a lot of spectra from different fibers with different fiber size. For example, SDSS spectra took from fibers of 3 arcsecond, 2D-FGRS spectra took from fibers of 2 arcsecond, etc. So we would like to recompute magnitudes to apertures that matched with the spectral ones, because in the photometrical catalog we have a lot of apertures, but usually they have size not the same as we need. So for most part of catalogs, we calculated aperture magnitudes using interpolation, and for Galaxy and WISE, where the spatial resolution is usually worse than the aperture size that we need, we calculated aperture corrections using 2D light profile from SDSS. Also, in our catalog, we have integrated photometry, and integrated photometry have some problems, because integrated photometry is just aperture photometry from apertures that are the same as galaxy size. And these apertures calculated in the different ways in different surveys. It can be calculated as Petrosian radius or as the Cron radius. And also all the surveys have different depth. So in different surveys, we collect flux of galaxy from different apertures, and the magnitudes of the same galaxy difference in different surveys. For example, on the slide you can see the galaxy with size from SDSS and Pan-STARRS, and you can see that Pan-STARRS size is more than SDSS size. The next problem is to convert our magnitudes into standard system. We know that filters of the set of filters in different surveys are different. So on the slide you can see SDSS filters and Pan-STARRS filters, and they have different official wavelength and other parameters. So we took as standard GALAX and SDSS and UKITS and WISE filters, and all the optical data we transform into SDSS filters, and all of the UKITS, all infrared data transform into UKITS filters. We used filter transformations from literature using transformations that based on correlation between difference in filters with colors. So we use this transformation and also shift our results to have zero difference between transformated filter and standard filter. So on the slide you can see that we have zero difference between transformated filter and standard filter on all the colors. And the last part of our work is to compute K corrections, because all the galaxies have different redshift, and it is necessary to consider that our flux and our spectral energy distribution shift due to this redshift. For galaxies with redshift less than 0.5, we calculating K corrections using Stilts function core, and for bigger redshift, it is necessary to calculate crossband corrections because flux from one filter due to redshift move to other filter. So we calculated crossband corrections by a polynomial function of one absorbed color and redshift. And on the slide you can see the example of our fit, and more about crossband corrections you can read in Anastasia Kasparova's poster. All the collected data we combined in PostgreSQL database, and every aperture photometry we bent with every spectrum. Also, one galaxy can have several spectra, and if we have two spectra, they can be from the same galaxy. So all the spectra have been combined into galaxies, and we make it used size from Hyperledger, Legacy Survey, SDSS, VST Atlas, and NST. For these reasons, we use PGSphere library in Postgres. And integrated photometry was bound with every object that we can find in our database. For first work of queries to our database, we create some foreign keys and indices. So here I can present the results. We create the RCSD-V2, that is the latest homogeneously processed catalog of extragalactic objects. Our catalog contains 4 and 7 million galaxies that have fully corrected photometric data from far UV to mid-infrared. Also, our catalog contains 5 and 7 million spectra that processed through nBurst full spectrum fitting algorithm. And for all of our galaxies, we have stellar population properties, emission line measurements, and in our website, you can find some interactive web interface to access the data. And more about our web development, you can now from Vladislav Klachkov talk. So if you are interested in RCSD-V2, you can hear our talk tomorrow, and also look at our posters that I highlighted in the slide. So thank you for listening. It's all.
Thank you very much, Victoria, for this excellent talk. We don't currently have any questions coming in through Discord. I don't know if there are any questions in the room. Yes, please go to the microphone so everyone can hear you online as well. Thank you.
Thanks a lot for a nice talk. I was interested to know whether you have a flag like these are the galaxies which are active or non-active in your catalog.
One second. So we work at the works that have been done on the basis of our catalog. We, for example, used active galaxies in some works, and we don't classify it in our catalog, okay. But you can look at the spectra in our catalog and other parameters, and by these characteristics, find the galaxies that you need by the parameters, and
okay, thank you.
Maybe classified it into active. Or
yeah,
not
it will be interesting to have those flags if I mean people who are interested in accessing the classification. Yeah. Thank you.
We not just have a classification in the catalog, but maybe we will make it next.
Yeah, thank you.
Thank you. There's a question being typed currently in Discord, so as soon as it appears, I will read it to you.
So, thank you. Bye.
Oh no, just there's one more question.
One more question?
It's just
sorry.
coming. They're still typing, you know. Yeah, exactly. Okay, the person is, it's Dirk. Dirk is not here in person, no. Okay, let's stop typing. Okay, so then I guess there's no other question. Thank you very much again. Thank you. Okay, and our final speaker for this session is Ivan Katkov, fast interactive web-based data visualizer of panoramic spectroscopic surveys. Take it away.
Hi everyone, I'm postdoc at New York University Abu Dhabi, as well as adjunct researcher at Moscow State University. First of all, thanks organizers to having me here, and I'd like to present another project from our exogalactic team, Vox Astra team. This is a tool for visualization of current panoramic spectroscopic surveys. So the motivation behind the project is that optical spectroscopy optical spectroscopy is very important for galaxy physics because it provides opportunity to get a lot of information about the galaxies. You can extract kinematics of stars, velocity dispersions, INS-GS kinematics, line ratios give you understanding of the abundance of the different elements, stellar population properties, and all bunch of these parameters. Considering a whole bunch of these parameters for large samples of galaxies covering different range of the galaxy mass and different environmental parameters provides a very unique basement for study galaxy evolution. And considering spatially resolved spectroscopy, it's more important because IFU spectroscopy provides much more information compared to aperture spectroscopy. That's why recently have been performed and released many IFU surveys, which are very useful for studies of galaxies. In our group, one of the main direction of research it's galaxy studies, and I personally interested in different aspects like searching for and study galaxies with kinematically decoupled structures, stellar quantum rotation, and galaxies with large-scale outflows. And all this project would be benefited from the tool where you can check is your galaxy or some sample of galaxies has appropriate IFU data, what's the quality of this data, and what's the result of the data products provided by different surveys or our own data products. And this is where IFU visualizer comes in. So this visualizer have roughly two parts, search and table view and detailed page view. Let's start from the first one. The heart of the search and table view is the input field where you can write your search query. And thanks to Django custom query package, you can able to write queries similar to where SQL clause. You can write relatively complicated queries which consist of different conditions using different comparison operators, non-strict comparison, between, in, combined in. We also support in simple mathematical operations between columns, and all these statements can be joined using logical operators and or. Also, this provides a possibility to have a kern search queries and using CSAM CDS server service to name resolution to the kern search. So, and let's go through the couple of examples. For instance, this query gives you a list of the spectral cubes taken from the SAMI survey for galaxies with declination less than 10 degrees. In operator is very useful if you have some preselected set of galaxies. For non-strict comparison, they're useful if you, let's say, you forget your favorite name of your favorite galaxy, but you remember that the name contains 6,4. Using this operator, you will find a bunch of the galaxies. Likely one of them would be your favorite galaxy. If you write down just NGC 4173, this query will be resolved as a kern search with default radius, and you will get spectral cubes for this particular galaxy. And another more complicated case, it helps you to preselect galaxies located in the Coma cluster, plus with condition on the GR color between 0.1 and 0.5. So it helps to select blue galaxies in Coma clusters. If you keen listeners can notice that in some of my screenshots, the list of columns in the table changed, and this is thanks to the column customization. If you click on the table settings, you will see a total list of the currently available tables available in the service. Expanding each table, you will see a list of the columns, and clicking on different columns, you can customize which columns will be presented in fully interactive table, which is sortable, scrollable, which makes some sense. Talking about Cube page, right now it has limiting functionality because our IFU visualizer is still under development. But here you use on the top few tabs where parameters from all available related tables to this particular spectral cubes are available. Then Aladdin Light with a set of buttons where you can quickly change imaging surveys, and clicking and on the Aladdin, it's also in the gray line, you see field of view of the spectral cubes, and clicking on different point of the galaxy, you will almost immediately retrieve galaxy from the retrieve spectra from the spectral cube, which will be fully interactive thanks for Plotly.js library. This is how our Cube page will looks like a little bit later. This is based. I'm showing you a screenshot from our first prototype of the IFU visualizer, which is called Manga Visualizer, and it provides access for manga data only, and you can see a lot of two-dimensional maps recovered from the spectral cubes. as well as spectra with best fit model, residuals, everything can be zoom in, zoom out, and also each panel and spectra has a setting button where you can change scaling adjustment, a type of color scheme, and so on and so on. Currently, in our visualizer, we have only 4 spectroscopic surveys: Manga, Sami, Khalifa, Atlas 3D, which contain roughly 10,000 spectral cubes, and later this number will be increased thanks to next forthcoming data release of the SDSS data DR17. And also we have some plans to add some Muse cubes, which are in the field of our interest from the scientific point of view. And let's go now through technologies which we used in this visualizer. First of all, our web application, it's a single page application. It means that upon initial request of this server, return basic HTML and JavaScript bundle, and then everything what you see on the screen controlled by JavaScript, making your user experience very smooth, because you no need to re-render HTML. And data comes from the server using asynchronous request directly to IP backend server. Their server decide based on business logic, should it retrieve data from directly database or from the spectral cubes, then serializing this data and return to the client. These are the list of all libraries, technologies we used in iView Visualizer. And speaking about backend, we based on the PostgreSQL database because of we would like to have current search queries which are supported by great extensions Q3C, PGSphere, and also would like to have integration with VO services. Which is one of our points for further development. And Django framework, Python-based, very popular, extremely well documented, which has a lot of batteries, which helps in some cases. But at the beginning, then we designing our IP, we decided to try to use a very popular nowadays GraphQL architecture for developing IP based on Django GraphEn library. It's nice because GraphQL provides only one endpoint, and killer feature is that you get exactly that result that you requested, minimizing overheads for serialization and transferring data. But it was surprisingly that simple Django REST framework provides 2-3 times faster query processing. And since Django has a very nice battery called Flex Fields, which mimicking a killer feature of GraphQL, that's why we decided to continue with Django REST framework, at least at the moment. And let's see, maybe later use cases might be better developed with GraphQL. We choose between React and Vue framework, but thanks to amazing Quasar framework, which contains a lot of components, data tables, buttons, panels, spinners, and so on, which makes designing of the interface like a charm, we of course decided to use Vue for this project. And we are developing our custom components. We are trying to focus, we are trying to make our custom components as clean as possible and separate logic to separate part of the retrieving data and post-processing of data in the state management of our application, and which makes our components clean and more representative. Currently, the status of the IFU visualizer is that we have very early stage of the development. Sometimes development like super intensive, I would say like violent, and some pieces of this part can be changed a little bit. And here is our next steps. First of all, we wanted to improve main cube page where details of the spectral cube can be considered, and this is a main place for visualization. Then we plan to provide additional data products, something similar that we are doing for RC-Site catalog. Of course, we have to add some VO compliant services. And I can't anymore separate you from the great time in Cape Town, and I would like to stop here and leave you these takeaway messages. Thank you so much.
Thank you very much for this very interesting talk. The only question we have currently is by Oleg. Maybe you can just ask it live.
Yeah, thanks very much for that. I was wondering, when I was looking at your web-based image visualization, did you happen to be in the Carta tutorial yesterday? And have you considered using something like Carta, or the other tool available is called JS9 for like browser-based FITS file viewing? Yeah. Because I think there's a lot of potential for integration there for this kind of thing.
Talking about Carta, Carta can be integrated, yes. Carta has some, well, what I saw yesterday, Carta is an amazing tool, and but as far as I understand, that the people who are developing Carta, they mostly focus on radio data. That's why, for instance, for my side, like a person who are doing research based on the optical spectroscopy, it's important, most important to see optical spectra, spectral profiler, which is, for Carta, you need to click many times to show this profiler. So this is my personal use case. And another important thing that our tool will provide opportunity to visualize our data products, which can be a little bit more complicated, like a spectral cubes plus different extensions containing, let's say, non-parametrical error recovered line of sight velocity distribution or something more. So doing our own instrument give us opportunity to make it as flexible as possible for our scientific goals.
Okay, thanks very much.
Thank you very much. Do we have any other questions in the room, maybe? And it doesn't seem like we are getting any more questions online either. So thank you very much again.
Yeah, thank you so much. Thank you.
And this marks the close of the first half day of ADAS 31. Oleg, I'll let you do any house calls. Thanks.
Just a reminder, dinner is at 7. Is it on? Okay. So just a reminder for everyone, dinner is at 7. It's going to be served up on the ground floor restaurant here, and the session starts at 8. So see you tonight. In the meantime, enjoy Cape Town.